Before Snickers, M&Ms and Reese's become candy, they go through a process designed to make them impossible to resist. Snickers is packed into dense layers of caramel. M&Ms are polished into irresistible shells, and Reese's Locks are sweet and salty together in a ridged cup. In this video, we dive into the hidden steps that turn these ingredients into three of the most addictive candies ever made. Roasted peanuts drop into a glossy caramel stream and turn it from a smooth ribbon into a textured, heavy layer. The caramel is warm, thick, and flowing slowly through a jacketed depositor. The peanuts enter at a controlled rate, so the layer has even distribution from edge to edge. Each piece becomes coated by caramel as the mixture folds through a short mixing section. The result is not a loose nut topping. It is a dense peanut caramel mass that will become the upper layer of a Snickers bar. The peanuts are prepared before they reach this point. Raw peanuts are cleaned, sized, roasted, cooled, and screened. Roasting drives off moisture and develops the nut texture. The hot peanuts pass through cooling air, so they become stable before mixing with caramel. Skins, fragments, and undersized pieces are removed, leaving a controlled peanut stream for the bar layer. The caramel begins separately in heated kettles or continuous cookers. Sugar, glucose syrup, milk ingredients, fat, and water are blended under heat. The mixture starts pale and fluid. As water evaporates, it thickens and darkens. The sugars concentrate, and the milk components help form the caramel color and cooked flavor. The caramel must be cooked to the correct body. If it is too thin, peanuts sink or spread unevenly. If it is too stiff, it will not deposit cleanly onto the nougat. The finished caramel needs to stretch during the bite, while still holding the peanut pieces in place. After cooking, the caramel moves through temperature-controlled piping. It stays warm enough to pump, but cool enough not to melt the layer beneath it. The roasted peanuts join the caramel just before depositing, so they remain separate, coated, and evenly suspended. The lower layer of a Snickers bar is nougat. Nougat starts with a cooked sugar syrup. Sugar, glucose syrup, and water are heated until the mixture reaches a high solids level. As moisture leaves, the syrup becomes thicker and more elastic. Temperature and concentration control the chew of the finished nougat. A separate aerated base is prepared in a heavy mixer. Egg albumin, or another whipping component, is hydrated and beaten until it can hold air. Hot syrup streams into this foam while the mixer turns. The heat stabilizes the foam, and the syrup strengthens it into a chewy mass. The mixture lightens as air is trapped inside. It becomes a dense confectionery foam rather than a liquid. Fat, milk components, peanut flavor elements, and other ingredients are added according to the formula. The mixer folds them in without collapsing the internal bubbles. The nougat must be soft, but not weak. It has to support the heavy peanut caramel layer above it and survive cutting later. If it is under-aerated, the bar becomes dense. If it is over-aerated, it can compress or separate under the caramel. The finished nougat leaves the mixer as a warm, elastic mass. It is transferred to a forming line. Rollers and spreading heads shape it into a wide, even sheet. Side guides keep the slab width controlled. The thickness is adjusted by calibrated rollers. The nougat sheet enters a cooling section. Cool air firms the surface and stabilizes the structure. The inside remains chewy, but the sheet becomes strong enough to carry the next layer. The peanut caramel mass now meets the nougat sheet. A wide depositor lays the warm mixture across the moving nougat. The caramel flows around the peanuts and spreads into a continuous band. Leveling equipment controls the height of the layer, so the finished bar has the right balance of nougat, caramel, and peanuts. The slab is now 2 layers moving as one. The bottom is pale, soft nougat. The top is darker caramel packed with roasted peanuts. The contrast in density is clear. The upper layer is heavier and more irregular. The lower layer is smoother and more aerated. The combined slab passes through cooling and setting. The caramel becomes less fluid. The nougat holds its shape. The peanuts lock into the caramel network. The slab must become firm enough for cutting while still remaining chewy inside. Cutting begins with lengthwise slitting. Circular knives divide the wide slab into long ropes. Each rope has the same cross-section. Nougat on the bottom, peanut caramel on top. The knives must pass through peanuts without dragging the caramel across the nougat face. The ropes are separated slightly so they do not stick back together. They then pass under a cross-cutting blade. The blade cuts each rope into individual bar lengths. The cutting action must be clean and timed with the conveyor speed. A poorly timed cut could stretch caramel strings or compress the nougat. The newly cut centers are not finished. Their sides are exposed, showing nougat, caramel, and peanuts. They need a complete chocolate coating. Before coating, the centers may travel through a conditioning zone. Air brings the surface to the right temperature. If the center is too warm, chocolate can slide or thin out. If it is too cold, chocolate can set before it spreads evenly. Milk chocolate is prepared in a separate process. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are mixed into a thick chocolate mass. The mixture passes through refining rollers that reduce particle size. This turns the chocolate from coarse to smooth. The refined chocolate moves into conching equipment. Heavy arms or rollers work the chocolate for a controlled time. The fat spreads around sugar, milk, and cocoa particles. The chocolate becomes more fluid and uniform. Before enrobing, the chocolate is tempered. It is cooled and warmed in a controlled sequence so stable cocoa butter crystals form. Tempered chocolate sets into a firm shell with the correct surface and snap. The Snickers centers enter the enrober on a wire mesh belt. A curtain of tempered milk chocolate falls from above. Each center moves through the curtain and chocolate flows over the peanut caramel top, down the sides, and across the nougat edges. Chocolate is also applied to the underside through the mesh belt. Excess coating drains through the belt and returns to the circulation system. The bar is now fully surrounded, but the shell still needs smoothing. Air blowers remove extra chocolate from the top and sides. The airflow controls coating thickness and rounds the bar's edges. It must not expose peanuts or leave thin spots. A vibrating section helps trapped air bubbles rise out of the coating and smooths the surface. The coated bars enter a cooling tunnel. Chilled air flows around them as they move forward. The chocolate changes from liquid to solid. The surface firms first, then the full shell sets around the soft center. Cooling must be controlled. Too much cold too quickly can crack the coating. Too little cooling leaves the shell soft and vulnerable to smearing. The tunnel balances air temperature, humidity, and belt speed until the chocolate is stable. At the tunnel exit, the bars pass through inspection. Cameras check shape, coating coverage, exposed center, broken peanuts at the surface, cracked chocolate, and incorrect size. Metal detectors scan the product stream. Any bar outside the programmed limits is rejected automatically. Accepted bars move to the wrapping section. Timing belts create even spacing. The bars align lengthwise before entering the flow wrapper. Printed film unwinds from a large roll. Tension rollers control its movement. Registration sensors read printed marks and synchronize the graphics with each bar. The film folds around the chocolate-coated bar through a forming box. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back of each pack, sealing and cutting one wrapped bar from the next. The wrapped bars pass through check weighers. A missing, broken, or incorrect bar causes the pack to fall outside the target range. Vision systems inspect seal quality, wrapper alignment, date code position, and print registration. Defective packs are removed from the line. A coding printer applies production information to the wrapper or outer package while the pack moves at high speed. The code is small and sharp, placed in a consistent location. M&Ms begin to look finished inside a rotating coding pan where plain chocolate centers slowly disappear beneath thin layers of colored sugar shell. The centers enter the pan as small, rounded pieces. They are not bright yet. They are smooth, brown, and fragile enough to need careful movement. The pan turns at a controlled angle, lifting the centers up its inner wall and letting them roll back down in a constant circular flow. A syrup line sprays a fine layer of sugar solution over the tumbling centers. The liquid touches the chocolate surface and spreads in a thin film. Warm, dry air flows through the pan and removes moisture from that film. As the water evaporates, sugar remains behind as a hard layer. This step repeats many times. The shell is not formed in one heavy coating. It is built through dozens of small additions. Each syrup dose lands, spreads, dries, and hardens before the next one is added. The pieces grow slightly larger with every cycle. The early layers are usually plain sugar. They seal the chocolate center and create a firm base. Without this base, later color coatings would look uneven and could absorb into soft spots. The tumbling motion keeps the pieces separated while each layer sets. The coating pan must turn gently but continuously. If it turns too slowly, the pieces coat unevenly and stick together. If it turns too aggressively, the centers chip or flatten. The sound inside the pan changes as the shell grows. Soft chocolate pieces first move with a muted rolling sound. As the sugar shell hardens, the movement becomes sharper and more rattling. Before the shell is built, the chocolate centers are made in another part of the factory. Chocolate begins as a mixture of cocoa ingredients, sugar, milk powder, cocoa butter, and fats. These ingredients enter a mixing system and form a thick paste. The paste is coarse at first because the sugar and cocoa particles are still too large. The chocolate mass passes through refining rollers. The rollers squeeze and grind the particles smaller. This step gives the chocolate a smoother texture. A gritty paste becomes a finer mass as it travels through the roller stack. The refined chocolate moves into conching equipment. Heavy mixing arms work the mass for a controlled time. Heat and movement smooth the chocolate, distribute fat around the dry particles, and develop the final flow behavior. The chocolate becomes glossy and fluid. The chocolate must then be tempered. Tempering controls the crystal structure of the cocoa butter. The chocolate is cooled and gently reheated through a precise sequence. Stable crystals form, allowing the finished center to set firm enough for coating. The tempered chocolate is deposited into small rounded shapes. It may be dropped onto chilled belts or into forming molds, depending on the line. Each deposit is measured so the centers have the correct weight and size. The small chocolate drops move through cooling. Chilled air or cold surfaces remove heat and solidify the pieces. The centers become firm but still sensitive to damage. Their shape must remain consistent because uneven centers create uneven candy shells. After cooling, the centers pass through screening. Pieces that are too small, too large, broken, or misshaped are removed. Accepted centers move into holding bins before shell coating. The centers now return to the coating pans. The first sugar layers begin building around them. Syrup is added in tiny controlled amounts. Air removes moisture. The shell thickens gradually. The pieces roll over one another without sticking because each layer dries before the next is applied. Once the foundation shell is complete, colored coating is introduced. Separate batches receive different color syrups: red, yellow, green, blue, orange, brown, and other colors are created by changing the color solution connected to the pan. Colored syrup coats the already hardened white or pale sugar base. The color deepens through repeated layers. The pieces do not become bright in one pass. the shade develops slowly as thin colored films stack over one another. Drying air is carefully balanced during coloring. Too much air can dry the syrup before it spreads evenly, leaving rough surfaces. Too little air can make the pieces sticky and cause them to clump. The pan controls air temperature, humidity, rotation, and syrup timing. After the color reaches the target shade, the candy pieces continue tumbling through finishing layers. These layers smooth the surface and prepare it for polishing. The shell becomes harder, more uniform, and more resistant to scuffing. The pieces now move to polishing pans. A very small amount of finishing glaze or polishing material is added while the candies tumble. The coating spreads over the shell surface in a thin film. The tumbling action buffs the candies against one another, producing the smooth shine associated with finished M&Ms. Polishing must not make the pieces sticky. The glaze is applied in tiny amounts, followed by drying and tumbling. The candy surface becomes glossy, but the pieces remain dry and free-flowing. After polishing, the candies are separated by color and inspected. Screens remove broken pieces, dust, and shell fragments. Airflow can lift away light particles. Optical systems can detect color defects, misshaped candies, dark marks, or chipped shells. Accepted candies move toward the printing stage. This is where the small white M is applied. The candies feed into mechanical orientation equipment. They pass through grooves, pockets, or rotating plates that position each piece so one flat side faces the printer. Because each candy is small and rounded, the machine must control movement precisely without cracking the shell. A pad printing system transfers the mark. A soft printing pad picks up white edible ink from an engraved plate and presses it briefly onto the candy surface. The pad flexes around the curved shell, leaving a clean letter. The printed candies move through a short drying section. Air sets the ink so the mark does not smear when pieces touch each other again. The printed M becomes part of the finished surface. The different colors are then blended into the final mix. Controlled feeders release each color in a programmed ratio. The streams join on conveyors or inside blending drums. The movement is gentle, so the polished shells and printed marks remain intact. The blend must remain even. Too many pieces of one color in a package would look inconsistent. The feeders meter the color streams continuously, and the blending equipment folds them together until the mix has the correct distribution. Peanut M&Ms follow a related but different center path. Instead of a chocolate-only center, roasted peanuts are selected, sized, and coated first. Each peanut has an irregular shape, so the early coating layers help round it before chocolate and sugar shell are added. The peanuts pass through roasting and cooling before coating. They are screened to remove broken pieces and undersized nuts. Chocolate is built around each peanut in layers, often through panning, until the center becomes smoother and more rounded. Then sugar shell coating, coloring, polishing, and printing follow the same general sequence. Peanut butter M&Ms use a shaped peanut butter center. The filling is mixed into a firm paste, portioned into small centers, cooled or conditioned, then coated with chocolate and shell. The center must be stable enough to survive tumbling in coating pans. For classic milk chocolate M&Ms, the accepted printed blend moves into packaging hoppers. These hoppers feed the weighers above the bagging machines. The candy is dense and free-flowing, so it moves more easily than fragile chips or puffs. But the polished shells still need controlled handling to avoid scuff marks. Multi-head weighers portion the candy. Small buckets collect measured amounts. The control system selects the combination of buckets closest to the target package weight. When the correct combination is ready, the buckets open and the candies drop into the bagger. The bagging machine starts with printed flexible film. The film unwinds from a roll and passes through tension rollers. It wraps around a forming tube, changing from a flat sheet into a vertical sleeve. a heat seal closes the back seam. The weighed M&Ms drop through the forming tube into the open bag. Horizontal sealing jaws close above and below the product. One seal forms the top of the filled bag, and the next forms the bottom of the following bag. A cutter separates each package from the film web. The sealed bag passes through check weighing. A bag outside the weight range is rejected. Vision systems check seal quality, print alignment, code position, and package shape. Coding equipment applies production information to the bag while it moves along the conveyor. Reese's peanut butter cups begin with peanuts being roasted until their raw firmness turns into a brittle, aromatic center ingredient. The peanuts move through cleaning and sizing equipment first. Screens separate small fragments, dust, and oversized pieces. Airflow removes light skins and loose material. The accepted peanuts continue as an even stream toward the roaster. Inside the roaster, hot air passes around the nuts while they move through the heating chamber. Moisture leaves the peanuts. Their texture becomes drier and more fragile. The color deepens slightly, and the internal oils become easier to release during grinding. The roasted peanuts exit hot and immediately pass into cooling. Air pulls heat away so the nuts stop roasting at the intended point. If they stayed hot too long, the flavor and color would continue changing. The cooled peanuts then move through another screening stage to remove broken material and remaining skins. The prepared peanuts enter grinding equipment. Rotating plates, stones, or rollers crush them into smaller particles. At first, the peanuts break into coarse pieces. Continued grinding releases peanut oil and turns the fragments into a thick paste. The paste becomes smoother as the particles are reduced. This peanut paste is not yet the Reese's filling. It is only the base. The finished center needs a dry, sweet, slightly grainy texture that holds its shape inside the chocolate shell. The peanut paste moves into a heavy mixer. Fine sugar is added in controlled amounts. Salt follows. Other formula ingredients are added to adjust texture, sweetness, and flow. The mixer arms fold the dry ingredients into the paste. The mass thickens as sugar disperses through the peanut fat. The filling becomes firm but workable. It does not behave like a loose nut butter. It presses together as a dense filling with a sandy, smooth bite. The mixer keeps turning until the sugar, salt, and peanut paste are evenly distributed from top to bottom. Temperature control matters during filling preparation. If the mass is too warm, it spreads too easily and loses its clean shape. If it is too cool, it becomes difficult to deposit. The filling is conditioned until it can be metered in precise portions. While the filling is prepared, chocolate moves through a separate system. Milk chocolate begins as a mixture of cocoa ingredients, sugar, milk components, cocoa butter, and fats. These ingredients are blended into a thick chocolate mass. The mixture is coarse at first, so it passes through refining rollers. The rollers reduce the size of sugar and cocoa particles until the chocolate becomes smooth. The refined chocolate moves into conching equipment. Heavy mixing arms work the chocolate under controlled heat. The mass becomes more fluid as fat coats the dry particles. The texture smooths out, and the chocolate develops the flow needed for depositing into paper cups. Before use, the chocolate is tempered. It is cooled and gently reheated through a specific temperature path. This controls the cocoa butter crystals. Properly tempered chocolate sets into a firm shell with a stable surface and clean bite. The chocolate is now ready to meet the paper liners. Stacks of fluted paper cups feed into a cup placing machine. The feeder separates one liner at a time and drops it into a metal or plastic pocket on a moving belt. Each pocket holds the liner open and supports its ridged sides. Rows of empty cups travel beneath the first chocolate depositor. Heated lines keep the tempered chocolate fluid as it reaches the nozzles. The depositor releases a measured amount into the bottom of each paper cup. The chocolate spreads outward from the center. It flows into the ridges of the liner and begins forming the bottom of the cup. A vibrating section shakes the tray gently, removing trapped air and helping the chocolate level. The line may use a spreading motion to push chocolate slightly up the sides. The goal is to form a lower shell that will support the peanut butter center. The chocolate must cover the base and lower ridges evenly. The partially filled cups enter a cooling section. Chilled air passes around the trays. The chocolate firms enough to hold its shape, but it is not treated as the final shell yet. It must still bond with the top chocolate layer later. The set chocolate bases return beneath the peanut butter depositor. The filling sits in a hopper above the line. A piston or rotary pump meters the dense peanut butter mass into exact portions. Each portion drops into the center of a chocolate-lined cup. The filling does not spread all the way to the paper wall. It lands as a compact disc or mound, leaving a narrow ring of chocolate exposed around the edge. This open chocolate ring is important because the top deposit must connect with it and seal the filling inside. The peanut butter deposit may be lightly pressed or shaped as it lands. It must sit level enough for the chocolate cover to form a smooth top. If the filling is too high, it can poke through the surface. If it is off-center, one side of the cup can have too much chocolate and the other too little. The cups now move beneath the second chocolate depositor. More tempered milk chocolate flows through the nozzles. A measured deposit lands on top of each peanut butter center. The chocolate spreads across the filling and reaches the exposed ring around the edge. It joins the base shell, enclosing the peanut butter. The top layer levels into a smooth surface, while the fluted paper liner defines the outer wall. Another vibration step settles the chocolate. Tiny air bubbles rise and break. The top surface becomes flatter and more uniform. The shell, base, and cover become one continuous chocolate enclosure around the filling. The fully filled cups enter the main cooling tunnel. Cold air removes heat from the chocolate while the trays move slowly forward. The chocolate crystals stabilize. The shell firms around the peanut butter center without melting or distorting it. Cooling must be controlled carefully. If the chocolate cools too quickly, the surface can crack or lose its smooth appearance. If it cools too slowly, the cups remain soft and can smear during wrapping. The tunnel balances air temperature, airflow, and belt speed. At the exit, the cups are firm enough for handling. The paper liner holds the ridged edge. The chocolate top is set. The peanut butter center is sealed inside, still dense and soft compared with the shell. The cups pass through inspection. Cameras check top coverage, missing chocolate, exposed filling, damaged liners, broken edges, and incorrect shape. Check weighing systems verify deposit accuracy. Metal detectors scan the moving product flow. Rejected cups leave the line automatically. Accepted cups move into orientation and grouping. For a standard pack, the cups are arranged in pairs. Conveyors guide individual cups into lanes. Timing belts position two cups side by side. The pair must remain aligned so the wrapper fits evenly and the cups do not overlap. Printed wrapper film unwinds from a roll. Registration sensors read tiny marks in the print so the design aligns with every pair. The film enters a forming section and folds around the cups. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back ends. The jaws seal and cut, releasing one finished pack from the continuous film. The wrapper protects the chocolate surface and keeps the pair together. It must be tight enough to hold the cups in position, but not tight enough to crush the ridges or deform the top. Ferrero Rocher is manufactured by assembling a layered sphere where a roasted hazelnut sits inside a wafer shell. The shell is filled with hazelnut chocolate cream. Then the whole piece is coated in chocolate and rolled in chopped hazelnuts before a final set and wrap. The process starts with hazelnut preparation because nut size and roast level define the center bite and also influence how the coating adheres. Raw hazelnuts are cleaned with screens and air separation, so stones and shells are removed. The nuts are graded by diameter, so the center nut fits the wafer cavity without forcing cracks. Roasting line heats the nuts to a target color and moisture. Roasting drives off water and develops aroma while keeping the nut interior crisp. After roasting, the nuts are cooled quickly, so residual heat does not soften the wafer later. Skins are removed after roasting because loose skin fragments create bitter specks and interfere with cream texture. Nuts pass through rubbers or abrasive rollers that loosen skins. Air aspiration lifts skins away from the heavier nut kernels. The cleaned nuts are then rescreened to remove broken pieces. Whole nuts are routed to center insertion. Broken nuts are routed to chopped nut streams or paste production. A portion of the roasted nuts is chopped for the outer layer. Chopping is done with calibrated cutters that create a narrow size band. The target size must be large enough to read as crunchy pieces. The target size must be small enough to adhere evenly to a wet chocolate surface. Chopped nuts are screened to remove fines because fines create dust and dull the finish. The chopped nut stream is held in dry, conditioned air so it remains free-flowing. Another portion of the roasted nuts is processed into hazelnut paste for the cream and chocolate phases. Nuts enter a grinding system where rollers or stone mills reduce them to a smooth paste. Grinding generates heat, so the paste line uses temperature control to avoid over-thinning. The paste is refined until particle size is below the gritty threshold. The paste is then held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a separate stream because wafer must be crisp and dimensionally stable. Wafer batter is prepared by blending flour with water and sugar and small amounts of fat. Mixing is controlled to hydrate flour while limiting gluten development. The batter is filtered to remove lumps that would block depositor nozzles. Batter viscosity is adjusted so it spreads evenly on heated plates. Wafer baking uses wafer irons that form thin sheets by heating both sides. The batter is deposited onto the plates and spread into a uniform film. Heat drives water out quickly and sets the wafer into a rigid, porous sheet. Baking time is tuned so the sheet dries to low moisture without scorching. The sheet exits and is cooled so it becomes crisp and easy to cut. To create the rocher shell, the wafer is shaped into cups or hemispheres. One method presses warm wafer sheets into molded cavities and then trims the edges. Another method bakes wafer directly into formed shapes using shaped plates. Forming must avoid cracks because cracks allow cream leakage. The formed halves are inspected by size and by edge integrity. Wafer halves are then paired into hollow spheres. A joining step applies a thin line of adhesive cream or chocolate along the rim. Two halves are aligned and pressed together. Pressure is controlled so the seam closes without crushing the wafer walls. The joined shells are cooled briefly so the seam sets and the sphere stays rigid during filling. The filling cream is produced as a fat-based emulsion with suspended solids. Sugar and milk solids are blended with hazelnut paste and cocoa components depending on the target profile. The mass is refined so it becomes smooth and spreadable. Refining can be done with roll refiners or ball mills that reduce particle size. The cream is then conched or mixed under heat to remove moisture and to distribute fat. Final viscosity is tuned so it can be dosed into wafers without air gaps. Chocolate used for coating is prepared and tempered for stable crystallization. Chocolate is melted and filtered to remove unmelted particles. Tempering cools the chocolate and builds stable seed crystals. The chocolate is then brought to a working temperature that maintains flow. Viscosity is adjusted by temperature control and by cocoa butter balance. Stable viscosity is needed because coating thickness must be consistent. Filling the wafer sphere begins by dosing a layer of cream into the cavity. The dosing head inserts into the shell opening and dispenses a controlled volume. The shell rotates or indexes, so cream spreads along the inner wall. This creates a base that will hold the center nut. The volume is controlled to avoid excess that would squeeze out at closure. A whole roasted hazelnut is then placed into the center. Placement uses a singulation system that feeds nuts one by one. Each nut is aligned and dropped into the cream bed. The cream supports the nut and locks it in position. Nut placement must be centered so the final sphere balances during coating. Off-center, nuts create wobble and uneven chocolate thickness. After nut placement, the cavity is topped off with more cream. The second dose surrounds the nut and fills remaining void volume. The dosing profile is tuned to avoid trapping air around the nut. Air pockets can collapse during cooling and cause surface dents. The cream surface is leveled, so the opening can be sealed cleanly. Sealing closes the filled sphere, so the cream is enclosed. A wafer cap or a chocolate plug can be applied depending on design. If a wafer cap is used, it is bonded with a thin film of cream and pressed into place. If a chocolate plug is used, tempered chocolate is deposited to create a seal. The seal must be strong enough to survive later tumbling and coating. After sealing, the filled spheres are cooled to firm the cream. Cooling brings the fat phase into a stable crystal state. It also reduces cream tack, so spheres do not stick during transfer. Cooling is staged, so wafer does not absorb condensation. Humidity control matters because wafer crispness must be preserved. Once the centers are stable, the line moves into chocolate enrobing. The spheres pass through a chocolate curtain or a dipping system. Chocolate coats the surface and also acts as the adhesive for chopped nuts. Excess chocolate drains off as the spheres roll on a wire belt. A controlled vibration can smooth the coating and release trapped bubbles. Air knives can trim excess and define a consistent thickness. Immediately after chocolate coating, the spheres enter a nut coating stage. Chopped hazelnuts are applied while the chocolate is still wet. The spheres roll through a bed of chopped nuts, or nuts are showered from above. Rolling ensures full coverage across the sphere. Nut feed rate is tuned, so coverage is dense but not clumped. Excess nuts fall away and are recirculated after screening. Nut adhesion depends on chocolate temperature and set speed. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slow, nuts can slide and form bare patches. The process balances chocolate temper and cooling tunnel entry, so the surface remains tacky long enough for nut embedding. After nut application, the pieces enter a cooling tunnel that solidifies the chocolate. The cooling profile is staged to promote stable crystals. Early cooling sets the surface quickly, so nuts lock in place. Later cooling pulls heat out, gradually, to avoid contraction cracks. Final exit temperature is set, so pieces are hard enough for wrapping. During cooling, the internal cream also equilibrates. The cream fat network continues crystallizing and becomes firmer. This improves bite and reduces oil migration. Temperature stability prevents bloom risk and keeps the outer finish glossy. The wafer remains protected because the chocolate and cream act as moisture barriers. Some lines apply a final polish to reduce loose nut dust. A gentle tumbling or airbrushing step can remove unattached fragments. This step improves pack cleanliness and reduces debris in wrappers. It also reduces scuffing during downstream handling. Sorting and inspection occur before packaging. Vision systems can detect incomplete nut coverage and shape defects. Weight checks confirm fill and nut presence. Rejects are diverted, so only uniform pieces reach wrapping. Metal detection can be used as a final integrity control. Cadbury chocolate begins as a controlled blend of cocoa components, dairy components, sugar, and fat that is refined into a smooth suspension, conched to stabilize flow and flavor, tempered to lock in stable crystals, then molded and packed, while temperature and viscosity stay inside a narrow window. Production starts with cocoa raw materials that arrive as beans or as processed cocoa ingredients, depending on the plant layout. When beans are used, they are cleaned first with screens and air separation, so stones and husk fragments are removed. The beans are then roasted in a programmed heat curve that drives off moisture and develops cocoa aroma while keeping scorch risk low. Roasting also makes the shells brittle, so separation is efficient later. After roasting, the beans are cracked and winnowed. Cracking breaks beans into nibs without pulverizing shells into fines. Winnowing uses airflow to lift lighter shell away from heavier nib. The nib stream is screened to remove oversized fragments that would strain grinders and to remove dust that would darken and overheat during milling. Nibs then enter grinding to become cocoa liquor. Grinding is a staged reduction where particle size drops while fat from the nib makes the mass flow. Early mills break nib into paste. Later mills refine the paste into a smoother liquor. Temperature is controlled because friction can raise heat and drive off aromatics. The goal is a stable liquor that is pumpable and consistent in solids and fat. Cocoa butter and cocoa powder streams are also managed. Cocoa butter is melted in jacketed tanks and filtered so no solid flakes remain. Cocoa powder is sieved to remove lumps that would create specks. These cocoa streams become levers for viscosity and flavor. More cocoa butter increases flow and melt. More cocoa solids increase intensity and thickness. Milk ingredients are prepared with the same attention to moisture and particle behavior. Milk powder is stored dry and sieved to break clods. Whey powders or lactose powders are handled similarly when used. These powders carry dairy flavor and also influence sweetness and caramel notes during later heating. Moisture in dairy powders must be low because water in chocolate drives thickening and seizing. Sugar is prepared as a clean, dry crystal feed. It is screened to control crystal size and remove agglomerates. Crystal size influences refining load and final mouthfeel. Fine sugar can reduce refining time but can increase dust and handling issues. Coarser sugar can slow refining and increase wear. The line selects a sugar specification that supports consistent refining performance. The first assembly stage is mixing, which creates a uniform pre-blend before refining. Cocoa liquor and melted cocoa butter enter a mixer and create a fat, continuous base. Sugar and milk powders are added gradually so they are wetted rather than floating as dry islands. Mixing uses a strong folding action to distribute powders through fat. The goal is a crumbly paste or thick dough depending on the recipe and the amount of fat present at this stage. In some milk chocolate processes, a crumb step is used to build characteristic dairy notes and to stabilize the milk solids. Crumb production combines milk and sugar with cocoa liquor or cocoa components and then heats the mixture to drive off water and develop flavor. The mixture is cooked until it becomes a dry or semi-dry crumb material. The crumb is then milled and later remelted into chocolate mass. This approach changes flavor and texture because it sets milk sugars in a different thermal history. Whether crumb is used or not, the downstream steps still require refining and conching. Refining is the step that turns the mixed paste into a smooth eating texture. Refining reduces the size of sugar and cocoa and milk particles so the tongue cannot detect grit. This is often done with 5-roll refiners or with alternative milling systems. In DUR, roll refining the paste passes between rollers with decreasing gaps. Each pass squeezes and shears particles smaller. The output becomes thin flakes because the mass leaves the final roll as a film that breaks off. Refined flakes have low free fat at their surface and are prone to holding moisture and air. They must be processed immediately into conching. Conching is a combination of mixing, shear, and controlled heat that changes both flavor release and rheology. In conching, the flakes are worked in a conche where paddles or rotors knead the mass. Heat keeps fat fluid and encourages volatile removal. Shear coats particles fully with fat, which reduces friction and lowers viscosity at a given fat level. Conching is often described as two overlapping goals. One goal is flavor smoothing by driving off unwanted volatiles and distributing aroma compounds. The second goal is flow control by reducing moisture and breaking down agglomerates so the chocolate becomes a stable suspension. Moisture control is critical because even small water content can cause thickening. Conches, therefore, manage airflow and temperature so water leaves gradually without overheating. During conching, emulsifiers can be added to fine-tune flow. Lecithin is a common flow modifier and it reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further at the same fat level. These additions are dosed late because early addition can mask conching effects and can change shear behavior. Dosing is precise because small changes alter how chocolate runs through pumps and through molding heads. After conching, the chocolate is held in storage tanks with gentle agitation. Tanks keep temperature stable, so the chocolate remains fluid. Agitation prevents separation and keeps the suspension uniform. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is smooth and flavored, but it is not yet in the right crystal state for molding. Tempering is the controlled crystallization of cocoa butter that creates a stable set and a clean snap. Chocolate contains cocoa butter that can crystallize in several forms. Only specific forms give the desired gloss and contraction. Tempering builds a population of stable seed crystals and then holds the chocolate at a working temperature where these seeds guide solidification. Tempering is done in continuous tempering machines that heat and cool the chocolate in stages. The chocolate is first heated to melt existing crystals fully. It is then cooled while being agitated so crystals begin to form. It is then gently reheated to melt unstable forms while keeping stable seeds. The output is a chocolate that flows well, but contains the right crystal seeds. Process control uses temperature sensors and viscosity signals to maintain stability. Once tempered, the chocolate is ready for shaping. For bars, the main shaping method is molding. Polycarbonate molds move under deposit heads that meter chocolate into each cavity. The depositor fills to a precise mass because bar weight must be consistent. Molds then pass onto a vibrating table. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate flow into sharp corners and improves surface gloss. After vibration, molds enter a cooling tunnel. Cooling is staged so the surface sets without shock. As chocolate cools, it contracts slightly. This contraction helps release from the mold. Cooling zones remove heat gradually so internal stress remains low. If cooling is too fast, the bar can warp or show bloom later. If cooling is too slow, throughput drops and molds remain occupied. When bars have solidified, they are demolded. Molds are flexed or tapped so bars release cleanly. The bars then move to inspection conveyors. Vision systems can detect surface defects and missing corners. Weight checks can confirm deposit accuracy. Defective bars are diverted for rework. Rework. Chocolate is collected and remelted, then reintroduced upstream in controlled ratios, so crystal history does not destabilize tempering. If the product includes inclusions like nuts or crisp pieces, the process adds an inclusion stage. Inclusions are prepared by roasting or drying and then screening to a tight size band. they are added either into the chocolate before molding or sprinkled into molds before depositing. Inclusion dosing must be consistent because it affects bar thickness and cooling time. Inclusion surfaces must be dry because moisture causes thickening and can create voids. If the product includes layered fillings, the line uses sequential depositing. A chocolate shell may be deposited first and partially set. A filling is deposited next. Another chocolate layer seals the top. This creates a composite bar that requires additional cooling time and more careful temper control. Even then, the same fundamentals apply. Each phase must flow at the right viscosity and set in the right order. Once bars are fully set, they move to wrapping. Wrapping is a mechanical process that protects chocolate from oxygen and moisture and from handling marks. Bars are fed into a flow wrapper or into a fold wrap system depending on the pack style. The wrapper forms film around the bar and makes seals. Seal temperature and dwell are controlled so the film closes without wrinkles. Film tension is controlled so it does not crush the bar edges. Toffee is manufactured by assembling a layered piece in a fixed cavity sequence where a caramel cup is formed first, a hazelnut is seeded into that cup, a hazelnut cocoa cream is deposited around the nut, and a final chocolate cap is applied before cooling and tray packing. Production starts with preparing the two high-volume mass streams that define the piece. One stream is a caramel that must be firm enough to hold a cup shape yet soft enough to bite cleanly. The other stream is a nut cream that must be smooth and pumpable, yet stable enough to keep its shape around the nut. A third stream is tempered chocolate for the cap and for any sealing functions. Caramel manufacturing begins with sugar and glucose syrup handling. Sugar is screened so crystal size is consistent and clumps are removed. Glucose syrup is held in jacketed tanks so viscosity stays stable for accurate pumping. Dairy components are prepared as a controlled liquid or powder stream depending on the recipe design. Fat is melted and filtered so it can be kneaded smoothly into the cook. Cooking is done in a continuous cooker or a batch kettle that is designed for high solids confectionery. The syrup phase is heated to dissolve sugar and drive off water. Solids level is the key target because it controls final chew and flow at the depositor. If solids are too low, the caramel will slump in the mold and stick in tooling. If solids are too high, the caramel becomes glassy and cracks when formed into thin walls. Temperature and residence time are tuned so browning develops to the desired level without scorching. As the cook reaches endpoint, the caramel is cooled to a working temperature where it remains plastic. Cooling is staged so viscosity is stable across the run. The caramel is held in a jacketed tank with gentle agitation to prevent skin formation. This tank feeds the forming depositor through heated pipes that avoid cold plugs. Flow meters and pressure sensors keep the depositor feed steady. Hazelnut handling runs in parallel. Nuts are cleaned and graded so the size band matches the cavity. Roasting drives moisture down and develops aroma while keeping the nut crisp. Cooling follows immediately, so residual heat does not soften caramel or melt cream fats later. Skin removal reduces bitter flecks and improves adhesion in the cream stage. Whole nuts are then singulated so they can be placed one by one. The hazelnut cocoa cream is prepared as a fat, continuous paste. Roasted hazelnuts are milled into a smooth nut paste with controlled temperature so oil does not separate. Sugar and cocoa solids and dairy solids are blended into this paste. Refining reduces particle size so the cream feels smooth rather than gritty. The cream is then mixed under controlled heat so viscosity becomes consistent and air is minimized. Emulsifiers can be introduced to tune flow and prevent oil bleed. The finished cream is held warm enough to pump but cool enough to keep flavor stable. Chocolate for the cap is produced and tempered to a stable crystal form. chocolate is melted and filtered, so no unmelted fragments remain. It is then tempered in a continuous tempering unit that heats and cools in stages. The goal is a chocolate that flows well but sets fast with gloss and clean release. Viscosity is monitored because cap thickness depends on flow through small nozzles. Assembly begins on a tray or belt line that carries a field of cavities. The cavities act as the master geometry for the product. Each cavity receives each component in sequence with tight timing. The first operation deposits caramel into each cavity as a measured shot. The shot is designed to form a cup rather than a flat puddle. This is done by using nozzle geometry and deposit motion that pushes caramel up the cavity walls. Immediately after deposit, a forming tool can shape the caramel cup. A punch or dome tool presses into the caramel to create a bowl profile. Tool temperature is controlled so caramel does not smear or stick. Dwell time is short, so the line speed remains high. The tool retracts and leaves a consistent hollow with a defined rim thickness. Caramel cup geometry is a major control point. Wall thickness must be thick enough to hold during nut insertion. Wall thickness must not be so thick that the bite becomes overly chewy. Rim geometry must be clean because the rim later interfaces with cream and the chocolate cap. If the rim is uneven, the cap can sit crooked and leave gaps. After cup forming, the cavities pass through a short cooling section. This cools the caramel surface to increase strength for nut insertion. Cooling is tuned to firm only the surface layer while keeping the bulk plastic. A fully hardened caramel would crack when a nut is pressed in. A too soft caramel would allow the nut to sink and deform the cup. Nut insertion follows. Nuts are fed from a singulator that orients each nut. A placement head drops or presses one nut into each caramel cup. Placement force is controlled so the nut seats at a consistent depth. The nut must be centered so the final piece balances. Off-center nuts can create thin caramel walls that tear. The nut is pressed enough to anchor without breaking the nut. Next, the nut cream is deposited around the nut. The depositor nozzle enters the cavity and dispenses a controlled volume. The cream must flow around the nut and fill the annular space. It must also avoid trapping air under the nut or along the cup wall. To control air, the deposit can be staged as a first ring and then a top fill. The nozzle motion can trace a small circle to wet the wall evenly. Cream viscosity is tuned for this step. If the cream is too thin, it floods and can overflow the rim. If it is too thick, it bridges and leaves voids. Void formation is a defect because it weakens structure and creates visual gaps under the cap. The line controls cream temperature tightly because temperature is the fastest way to shift viscosity without changing formulation. After cream deposit, the surface is leveled. A small leveling blade or vibration can flatten the cream surface. Leveling ensures the chocolate cap will sit evenly. It also ensures the cap seals the cavity edge without a high spot that would break later. Leveling is gentle because excessive vibration can move the nut and distort the cream ring. Chocolate capping follows immediately after leveling. Tempered chocolate is deposited as a disc onto the cavity opening. The disc must bond to the cream and rim and then set without cracking. Deposit weight defines cap thickness, which controls snap and protects the interior. If the cap is too thin, it can fracture during tray packing. If too thick, it can dominate the bite and slow setting. To achieve a clean cap, the chocolate is deposited at a temperature where it spreads slightly, then stops. The mold geometry helps define the cap edge. Some lines use a light vibration after capping to remove bubbles and ensure contact. Vibration must be limited because it can cause chocolate to run down the cavity walls and change appearance. 3 Musketeers bars are built by producing an aerated chocolate nougat center and then coating it in tempered milk chocolate before wrapping. The factory line is arranged so the nougat stream runs continuously into forming and cutting, while the chocolate stream runs continuously through tempering and enrobing. Both streams are tuned to match temperature, viscosity, and throughput, so the coating seals cleanly around the center without sink marks or edge splits. The milk chocolate coating begins with bulk ingredients staged for refining and conching. Granulated sugar is screened to a narrow particle size range so the roller refiner can produce a predictable grind. Cocoa liquor is preheated to lower viscosity and allow accurate pumping into the mixing tank. Cocoa butter is melted in jacketed vessels and circulated through filters to remove any solid crystals that could seed unstable texture. Milk powder is fed from sealed bins and is deagglomerated in a low shear disperser so it hydrates into the fat phase without forming dry nodules. Lecithin is held in a small day tank and is dosed late so it reduces viscosity after the primary particle size reduction. Vanilla or vanillin is stored as a concentrated liquid and is metered as a final flavor addition to avoid volatilization during extended heat exposure. A premixer combines cocoa liquor, a portion of cocoa butter, and sugar into a thick paste that can be refined. The paste is pumped to a 5-roll refiner, where it is squeezed into thin flakes that fracture sugar crystals and cocoa particles to a controlled fineness. The gap settings on each roll stage determine final particle size distribution, which controls mouthfeel and flow at enrobing. Refined flakes fall into a feed chute that meters into a conch. The conche applies heat and shear to drive off undesirable volatiles and to coat particles with fat. During conching, the remaining cocoa butter is added in increments to reach target viscosity without flooding the mass too early. Milk solids are blended in, so lactose and milk proteins are dispersed uniformly without scorching. Lecithin is added near the end to adjust yield value and plastic viscosity to match curtain requirements at the enrober. After conching, the chocolate enters a holding tank with gentle agitation that prevents separation and keeps temperature stable. From the tank, it flows to a tempering system that builds the correct crystal structure in the cocoa butter. The chocolate is heated to fully melt existing crystals, then cooled through a controlled zone to form stable seed crystals. It is then slightly reheated to remove unstable forms while preserving the stable fraction. The tempered chocolate exits at a narrow temperature band where viscosity is low enough for enrobing yet crystal content is high enough to set quickly on cooling. Inline viscometers monitor flow and trigger cocoa butter trim additions if the chocolate thickens. Filters ahead of the enrober remove stray solids that could block the curtain slot or imprint the coating surface. The aerated center starts as a sugar syrup system designed to whip into a stable foam. Granulated sugar is dissolved in hot water in a steam-jacketed cooker where temperature is driven to a target solids level. Glucose syrup or corn syrup is pumped in to reduce crystallization and to keep the finished nougat soft. The syrup is cooked under controlled pressure, so boiling is efficient and the concentration is repeatable. When the syrup reaches its target, it is discharged through a flash cooling step that drops temperature enough to prevent overcooking while preserving fluidity for mixing. The syrup then enters a continuous aeration mixer where it meets foaming proteins and fat. The foaming phase can be based on egg whites or protein blends that create a thin film around air bubbles. Liquid egg white is filtered and tempered so it whips predictably without breaking. If dried albumin is used, it is rehydrated under high shear and allowed to rest so hydration is complete before aeration. Proteins enter the mixer where high-speed rotors incorporate air while controlling bubble size distribution. Bubble size is managed by rotor speed, back pressure, and viscosity, which together determine the final density of the center. A small amount of fat is introduced to soften texture while not collapsing foam. Emulsifiers are used to stabilize the air cells and reduce drainage of the syrup phase. cocoa, or chocolate flavor components can be blended into the center so the interior tastes like light chocolate rather than plain vanilla. The aeration mixer operates as a pressurized system, so air injection and shear can be controlled precisely. Compressed air passes through sterile filters, then through a mass flow controller that sets the air rate per kilogram of nougat. The mixer creates a continuous foam stream that is metered to the forming section. Density is checked by inline measurement that compares mass flow to volumetric flow. If density drifts, the system adjusts air rate or syrup feed to recover. Temperature of the foam is controlled because warm foam collapses and cold foam stiffens before forming. A heat exchanger may be used on the syrup line to fine-tune final foam temperature at discharge. Once aerated, the nougat is sent to a depositor or extrusion head, depending on the specific forming method. In an extrusion layout, the foam is pushed through a slot die that creates a wide ribbon with a controlled thickness. The ribbon lands on a moving belt that has a release surface to prevent sticking. Belt speed is synchronized to extrusion flow, so thickness stays constant across the width. A leveling roller may follow to flatten the ribbon and to remove surface waves. The ribbon then passes under a conditioning tunnel where temperature is reduced gradually, so structure firms without creating a brittle skin. This conditioning step sets the foam walls enough for clean cutting. The nougat sheet is cut into bars using a guillotine or rotary slitter system. Longitudinal knives create parallel lanes with precise width. A transverse guillotine cuts each lane into individual pieces at the target weight. Knife timing is servo-controlled to keep cuts aligned even if belt speed changes slightly. Scrap from edge trim is collected and recycled back into the aeration mixer in controlled ratios so density remains stable. Bar weight is checked by dynamic scales that weigh each piece at speed. Out of tolerance, bars are removed by air jets that divert them into a rework stream. Before coating, the centers may pass through a brief pre-coat step. A thin layer of chocolate can be applied to reduce moisture migration and to improve adhesion of the final coat. This pre-coat is often applied as a bottoming film or a partial curtain. The centers then enter a short chill zone that sets the pre-coat so the bar can handle the stress of full enrobing. Surface temperature at enrobing is managed because a warm center can thin the coating and cause weak corners. A cold center can cause premature thickening and a rough surface. The line therefore targets a specific center surface temperature that balances flow and setting. Enrobing is performed by sending each nougat center through a chocolate curtain. The tempered milk chocolate flows from a header tank into a curtain slot that produces a uniform sheet of chocolate. The bar passes under the curtain and receives top and side coverage in a single pass. A bottoming wheel or bottomer reservoir coats the underside and closes the seam. Immediately after, coating the bar rides over a vibrating section that removes excess chocolate and levels the coat. Air knives blow controlled air across the surface to thin the layer and to sharpen edges. Air pressure is tuned so it does not expose the nougat at corners. The chocolate runoff is collected and returned to the tempering circuit where it is re-tempered before reuse. Decorative top marks can be added while the coating is still fluid. A striping head deposits thin lines of chocolate across the top to create the characteristic surface pattern. The striping chocolate is tempered separately to match viscosity and to prevent bloom in the stripes. Nozzles are aligned to bar lanes, so stripes land consistently. Flow is controlled by servo pumps that pulse for each bar group. Stripe height is kept low, so it does not crack during cooling or wrapping. After enrobing the bars, enter a cooling tunnel that sets the chocolate crystal network. Cooling is staged in zones to control contraction and gloss. An initial zone cools gently so the surface does not freeze before the interior sets. A middle zone cools more strongly to lock in crystal structure and to prevent deformation. A final zone equalizes temperature so the bar exits without condensation risk when exposed to ambient air. Conveyor speed and tunnel temperature define residence time. If residence time is too short, the coating remains soft, and fingerprints during handling appear as dull marks. If residence time is too long, the bar can overcontract and pull away at the seam. Kit Kat bars are manufactured by building crisp wafer sheets in continuous ovens, then layering them with fat-based cocoa cream before cutting fingers and enrobing them in tempered chocolate. The line is designed so wafer output is buffered to match chocolate throughput. The process starts with a batter system tuned for rapid baking and controlled porosity. Wheat flour is conveyed from silos to a sifter that removes bran specks and compacted lumps. The sifted flour drops into a day bin that feeds a high-speed whey hopper. Cornstarch may be blended into the flour stream to reduce gluten development and to increase snap after baking. Leavening is dosed in small quantities because wafer rise must be minimal and uniform. Salt is metered finely so it dissolves fully in the batter water phase. Sugar is used at a lower level than cake because wafer structure relies on starch gelation and moisture removal rather than sweetness. Liquid water is tempered to stabilize viscosity and to prevent seasonal drift in batter flow. Vegetable oil or melted fat is held in jacketed tanks and pumped with gear pumps for repeatable dosing. Emulsifiers are added to improve plate release and to help the batter spread thinly across hot surfaces. A portion of batter may include recycled wafer trim ground to a fine meal and hydrated to keep waste low without adding grit. Batter mixing is performed in a continuous mixer or in a batch mixer with rapid turnover, depending on line scale. Dry ingredients are blended first, so leavening and salt are dispersed before liquids arrive. Liquids enter through multiple injection points, so flour hydration occurs quickly without dry pockets. The mixer uses high shear at the inlet and lower shear near discharge to avoid excessive gluten formation. Batter temperature is controlled because warm batter thins and overspreads, while cold batter thickens and causes uneven fill. Viscosity is measured by inline torque or pressure drop and adjusted by microdosing water. A deaeration step may follow mixing to remove large bubbles that would create blisters in the wafer sheet. The finished batter is pumped to a feed manifold that supplies the baking machine with constant head pressure. Wafer baking uses paired heated plates that close to a precise gap and imprint a grid texture. The plates are heated by gas burners or thermal oil circuits and are held within tight temperature tolerances across the surface. Batter is deposited onto the lower plate by a dosing head that measures volume for each plate cavity. The top plate closes and spreads the batter into a thin layer that fills the pattern relief. Baking begins instantly as water flashes into steam and the starch begins to set. The plate set moves through a tunnel oven where heat continues to drive moisture out while browning remains controlled. Venting removes steam so it does not condense on cooler machine sections and drip onto new plates. Plate pressure and gap determine wafer thickness, which later determines finger count per bar and final snap. Bake time is tuned so moisture drops low enough for crispness, yet not so low that the sheet becomes brittle during handling. When plates open, the baked wafer sheet releases and is transferred onto a cooling conveyor. The sheet passes under fans that equalize temperature and prevent trapped heat from softening the crisp matrix. Sheet moisture is measured indirectly by near-infrared sensors that scan across width. Any drift triggers changes in oven speed or plate temperature to recover the target. Wafer sheets are fragile, so conveyors use low impact transfers and short drops. Alignment guides keep sheets square for the next operation. Scrap edges and broken sheets are separated and routed to a grinder for controlled reuse. Layering begins with preparation of the cocoa cream that bonds wafer sheets into a multi-layer block. This cream is a fat continuous paste rather than a water-based filling. Sugar is milled to a fine powder and blended with cocoa powder to form a dry premix. Cocoa butter and vegetable fats are melted and filtered to remove crystals that would make the paste grainy. The dry premix is added into the melted fat in a mixing tank with strong agitation. The mixture then passes through a roll refiner or bead mill to reduce particle size and to improve spreadability. Lecithin is added late to reduce viscosity and help the paste wet the wafer surface quickly. Flavor is added at the end to preserve volatile notes. The finished cream is held in a jacketed buffer tank at a temperature that keeps it fluid but not so hot that it seeps deeply into wafer pores. Cream application uses a spreader system with metering rollers. A wafer sheet enters the station and passes under a curtain or roller that lays down a precise film thickness. The film thickness is controlled by roller gap and by paste viscosity. Another wafer sheet is placed on top by a pick and place unit that aligns edges. The sandwich passes through a compression section that ensures full contact without crushing the wafer cells. This layering repeats to build a block with multiple wafer layers separated by thin cream layers. The number of layers determines the final finger height and bite. Registration is critical because misalignment causes exposed wafer steps after cutting and uneven coating. After stacking, the wafer block enters a setting tunnel where the cream partially crystallizes to lock layers together. Temperature is reduced in stages to avoid warping from rapid contraction. The block is supported on a flat belt to maintain planarity. Block hardness is monitored by deflection sensors that measure how much the block bends at a given support span. When the block reaches a target firmness, it moves to cutting. If the block is too soft, blades smear the cream and pull crumbs. If the block is too hard, blades chip wafer edges and create dust. Cutting converts the block into long logs and then into fingers. A first set of rotary knives or ultrasonic blades slices the block lengthwise into bars that match the finger group width. Blade spacing is adjustable for different formats, like 2-finger or 4-finger packs. A second cutter slices the bars into individual finger lengths. Blade timing is synchronized to belt motion to prevent diagonal cuts. Crumb extraction hoods collect wafer dust so it does not contaminate chocolate surfaces later. Trim pieces are segregated because they can be reworked into wafer meal or into cream base depending on quality. The cut fingers are transferred gently to avoid cracking along the wafer grid. Before enrobing, the fingers may receive a base coat to improve seam closure. A bottoming bath lays chocolate onto the underside as the finger rides over a wheel. The wheel transfers a film and then excess is wiped to a controlled thickness. The pre-coated fingers pass through a short cooling zone so the base sets enough to support the full coat. Surface temperature is controlled because warm fingers thin the chocolate layer and cold fingers cause thick buildup at edges. Chocolate coating starts with production of the milk chocolate used for the shell. Sugar, cocoa liquor, cocoa butter, and milk solids are mixed and refined to a target particle size. Refining is done on roller refiners that produce flakes for conching. Conching applies heat and shear to coat particles with fat and to reduce harsh notes. Lecithin is added to tune flow for enrobing and to reduce yield stress. The chocolate is then tempered to create stable cocoa butter crystals. Tempering follows a melt-cool-reheat profile and is controlled by temperature sensors and viscosity feedback. The tempered chocolate is held in a header tank that feeds the enrober curtain at constant pressure. Enrobing covers the wafer fingers with a continuous curtain of tempered chocolate. Each finger passes through the curtain and gets top and side coverage. A bottoming section ensures the underside is sealed and eliminates bare spots at the edges. Vibrating conveyors level the coating and release trapped air at corners. Air knives shape the final thickness and clear chocolate from the finger grooves where excess would bridge the separations. Runoff chocolate is collected and returned to the tempering loop so crystal structure remains correct. Some formats add a chocolate line between fingers to strengthen the breakpoints, and this is done by targeted deposition nozzles before final cooling. Cooling tunnels set the coating without causing bloom or warping. The tunnel is divided into zones that control the rate of crystal growth. Early cooling stabilizes the surface gloss. Middle cooling builds strength through the thickness. Final conditioning equalizes temperature so wrappers do not trap condensation. Conveyor speed sets residence time and is matched to coating thickness. If cooling is too aggressive, the chocolate contracts unevenly and can crack at the corners. If cooling is too mild, the coating stays soft and picks up belt marks. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow-metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion, with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, the mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm, depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill-seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems. The Heath chocolate process starts with ingredient staging for the toffee kettle, because the toffee is the structural backbone. Sugar is received as dry crystals and screened to remove clumps. Corn syrup is held in jacketed tanks to keep viscosity stable and to meter accurately. Butter is melted under controlled heat and filtered to remove any milk solid aggregates. Water is tempered to a consistent temperature because it affects dissolution rate. Salt is weighed precisely because it changes perceived sweetness and also shifts how the boil behaves. If almonds are used on the core, they are roasted, cooled, and size graded in parallel so they can be applied at the correct moment later. A dissolving stage forms the first syrup. Sugar and water are combined and heated with agitation until the solution becomes clear. The goal is complete dissolution, so no crystals remain to seed early crystallization. Corn syrup is blended in as a crystallization control tool. It reduces unwanted graining and helps the final toffee fracture as a clean glass rather than crumble as a sandy mass. The mixture then enters a high solids cooking phase in a steam-jacketed kettle or a continuous cooker. Cooking is managed as a concentration process. Heat drives off water and raises the syrup to a specific solids level where it will set hard. Temperature is used as an endpoint proxy because at constant composition, boiling temperature rises as water leaves. The cook profile is tuned so the syrup thickens steadily without scorching at the kettle walls. Scraped surface agitation or strong wall sweeping paddles can be used to keep the hottest surfaces clean and prevent localized burn. Butter is introduced at a defined point rather than from the beginning because fat changes heat transfer and can interfere with dissolution if added too early. Once the syrup reaches a certain concentration, melted butter is metered in and mixed rapidly. The mixture becomes a fat in syrup emulsion. The fat contributes flavor, and it also changes fracture behavior by plasticizing the sugar glass slightly. Butter addition is controlled tightly because too much fat yields a softer toffee that smears under cutters. Too little fat yields a brittle, overly sharp glass that shatters into dust. As concentration continues, the emulsion thickens and begins to take on the characteristic toffee behavior. The process controls agitation intensity to keep the emulsion stable and to prevent phase separation. If fat separates, the surface can become greasy and the final slab will have weak layers. The kettle continues cooking to a final endpoint defined by temperature and by viscosity behavior at discharge. When the endpoint is reached, the toffee is discharged quickly to stop further concentration. The discharge goes to a depositing system that spreads the hot toffee into a thin sheet. A steel cooling belt or a slab table is used. Deposit rate and belt speed set sheet thickness. Thickness is critical because it determines cooling rate and later break size. A thicker slab retains heat longer and stays pliable, which can cause bend and smear. A thinner slab cools quickly and can become too brittle, producing dust. If almond topping is part of the product, it is applied while the toffee surface is still tacky. Roasted almonds are spread across the sheet with a calibrated spreader. A light press can embed the nuts into the surface so they lock in place. Press force is controlled because excessive force can push nuts through and create stress points that crack during breaking. Timing is precise because if the toffee skins over before nut application, adhesion is weak and almonds will fall off later. Cooling sets the toffee. Cooling is staged to remove heat evenly through the thickness. Rapid surface cooling with a warm interior can create internal stress that later causes random cracking. A controlled profile cools the sheet uniformly so it becomes a stable glass. As it cools, the toffee transitions through a glass transition zone where it goes from rubbery to brittle. The line targets a specific exit temperature where it is hard enough to fracture predictably, but not so cold that it becomes explosively brittle. Once cooled, the sheet is moved into a breaking and sizing system. Heath-style bars often require small pieces or segments rather than long sticks. The sheet can be cracked by rollers that apply controlled compression. The first break produces large pieces. A second reduction stage brings pieces to the target size. Screens separate oversize and fines. Oversize is returned to the breaker. Fines are removed because they create dust and can interfere with chocolate coating quality. Conditioning is used after breaking because freshly fractured toffee can carry temperature gradients and surface microcracks. Conditioning allows the pieces to equilibrate in a controlled environment. This stabilizes brittleness and reduces later fracture during conveying. It also reduces the risk of surface moisture pickup because sugar glass is hygroscopic and can become tacky if exposed to humid air. Chocolate coating is prepared in a separate system. Chocolate is melted, filtered, and tempered if real chocolate is used. Tempering creates stable cocoa butter crystals so the coating sets with gloss and resists bloom. Working temperature is held tightly because viscosity determines coating thickness and coverage. A stable coating thickness is important because toffee pieces have sharp edges that can poke through thin chocolate. Coating is applied by enrobing or panning depending on piece format. For bar segments, enrobing is common. Pieces are conveyed through a chocolate curtain that coats the top and sides, while a bottoming system coats the underside. Excess drains through a wire belt. Air knives remove excess and smooth the surface. Air knife pressure is tuned so it does not expose toffee corners. For bite-sized pieces, panning can be used where pieces tumble while chocolate is applied in stages. After coating, pieces enter a cooling tunnel. Cooling is staged to set the chocolate surface quickly and then crystallize the interior gradually. This prevents cracks and bloom. The cooling tunnel must also keep humidity controlled to prevent condensation, which can cause sugar bloom on the chocolate surface. Exit temperature is set so pieces are hard enough for packaging without scuffing. Packaging begins with portioning and protecting against moisture. Chocolate-coated toffee is vulnerable to humidity because moisture can soften toffee over time. Packaging films are chosen for moisture barrier performance. Multi-head weighers portion target weights. Drop heights are minimized because impact can fracture toffee inside chocolate and create internal cracks. Bags are sealed with controlled timing to keep pieces out of the seal area. Cartons and multi-packs add physical protection. After the toffee sheet leaves the primary cooling belt, the line treats it as a brittle engineering material that must be fractured in a repeatable way. The goal is not just break it, but break it so the average piece mass, edge sharpness, and dust generation stay within a narrow band. This is important because the chocolate coating step cannot compensate for extreme variability. Oversized chunks will not coat evenly and will jam conveyors. Excess fines will contaminate chocolate and weaken package seals. The sheet is first transferred from the cooling belt to a feed table that controls the entry rate into the breaker. Transfer is done with minimal bending. Bending introduces stress lines that can cause unpredictable fractures later. The feed table can include a slight pre-warm or hold zone if the sheet has cooled too far. This is not to soften it, but to bring it back to the target brittleness window, where fracture produces chunks rather than powder. Primary breaking is commonly done with counter-rotating rollers or a tooth cracker. The rollers apply compressive force that initiates cracks along the natural weakness lines in the sugar glass. Gap setting is the main control. A wide gap produces larger shards and fewer fines. A narrow gap increases size reduction but also increases dust. Roller surface texture matters. Smooth rollers crush more uniformly but can slip on glossy toffee. Textured rollers grip better but can create more microfractures. Throughput rate is also a factor. High feed rates force pieces to stack and crush unpredictably. Low feed rates yield cleaner fractures but reduce capacity. The line balances. These so the output after the first stage is large, manageable chunks with limited dust. Those chunks then move to a secondary reduction stage if the product format needs smaller pieces. This stage is tuned differently than the first. Instead of simply cracking the sheet, the objective is to trim the size distribution toward a target. A common approach is a second roller crusher with a tighter gap. Another approach is a breaker with oscillating bars that apply repeated impacts. Impact-based systems can create more fines, so they are tuned to deliver enough energy to break oversized pieces without pulverizing the entire stream. Some lines split the stream, sending only oversized pieces to higher energy reduction and passing acceptable pieces forward to avoid unnecessary damage. Immediately after reduction, screening classifies the output. Vibratory screens are arranged in decks. The top deck retains oversize. The middle deck passes the target fraction. The bottom deck collects fines. Oversize is routed back to the secondary breaker. Routing is controlled to avoid endless recirculation that would overwork material and generate dust. Fines are usually removed from the primary product stream. They may be recycled into other confectionery streams or blended back in at very low ratios if allowed, but they cannot dominate because fines behave like powder in chocolate. Dust control is a constant feature at this point. Air aspiration hoods pull airborne sugar dust away from the line. Dust is not just a cleanliness issue. Sugar dust is hygroscopic. It absorbs moisture and becomes sticky. Sticky dust builds up on belts and changes friction, which increases breakage. Dust also contaminates chocolate later and makes coating surfaces rough. Therefore, the plant often uses localized vacuum extraction at the breaker discharge and at screens. The extracted dust is captured in filters and removed. Piece temperature is monitored after breaking because warm pieces behave differently in chocolate than cold pieces. If pieces are still warm, their surfaces can soften slightly and pick up dust. They can also melt chocolate at contact points later and create thick patches. If pieces are very cold, they become highly brittle and can fracture during conveying and enrobing, creating internal cracks that later show as broken pieces in the bag. The line therefore includes a conditioning conveyor or bin, where pieces sit under controlled air long enough to equalize. Conditioning air is kept dry. If humidity rises, the toffee surface can take on moisture and become tacky, which will cause clumping during coating. At this stage, almonds, if present, are checked indirectly through process behavior. Almond density affects how pieces roll and how they feed. If almond coverage is too high on the sheet, some pieces will have heavy nut clusters that act like rigid protrusions. Those protrusions can act as stress concentrators and cause the piece to fracture more easily at the nut boundary. They also create irregular geometry that is harder to coat. To manage this, nut spreaders earlier are set to deliver a uniform coverage rather than piles. During breaking, screen sizing is often adjusted slightly to compensate for the irregular shapes created by nuts. Before the pieces see chocolate, the line may add a quick surface stabilization step. This can be as simple as a short dry air tunnel that removes any superficial humidity absorbed during transfer. It can also include a very light dust removal step using rotating brushes or air jets. The goal is to present a clean, dry, relatively dust-free surface to the coating system. A dusty surface causes two problems. It thickens the chocolate locally by absorbing cocoa butter, and it creates weak adhesion zones where the chocolate can flake. Chocolate coating preparation runs in parallel and must match the flow of toffee pieces. Chocolate is held in a melt tank and then fed to a tempering unit if real chocolate is used. Tempering is controlled by staged heating and cooling that builds stable seed crystals. The working chocolate then enters the enrober reservoir. Viscosity is checked indirectly through pump pressure and curtain behavior. The enrober is adjusted so the curtain thickness matches the intended coat weight. For a toffee core, coat thickness must be enough to cover sharp edges and to provide a continuous moisture barrier. Too thin and corners poke through, leading to pinholes. Too thick and the bar becomes heavy and loses the toffee to chocolate balance. The enrobing conveyor is set up to minimize impact. Pieces enter the curtain in a single layer with controlled spacing. If pieces collide under the curtain, they can stick together through wet chocolate and form doubles. Doubles create packaging issues and are often rejected later. Spacing is therefore created with flighted belts or lane dividers before the curtain. When pieces pass through the chocolate curtain, the top and sides are coated first. The underside is coated by a bottoming system, either a chocolate bath or a bottoming roller that applies a film from below. The thickness of the bottom coat is important because toffee pieces tend to have sharp edges that can cut through thin bottoms as they settle onto belts. A wire mesh belt allows excess chocolate to drip away. Immediately after the curtain, air knives blow across the surface to remove excess and smooth the coat. Air pressure is tuned carefully. Too strong and it exposes corners. Too weak and it leaves heavy pooling at the base. After enrobing, the pieces enter the cooling tunnel. Cooling begins with a quick surface set, so the coating stops flowing and the pieces do not flatten into the belt. Then cooling becomes more gradual to crystallize the interior of the chocolate in a stable form. Humidity control in the tunnel prevents condensation that would cause bloom. Exit temperature is set so the coating is hard enough for handling, but not so cold that pieces become brittle and crack internally at the toffee core during packaging drops. After the coated pieces leave the enrober, the cooling tunnel becomes the main tool for locking both appearance and long-term stability. Chocolate is not simply chilled until hard. The coating is guided through a temperature profile that creates the right crystal structure while avoiding stress, cracks around the toffee edges, and around any embedded nut fragments. The first cooling zone is designed to set the surface quickly. Fast surface set prevents the chocolate from continuing to flow and pooling at the base, which would create thick feet and uneven thickness. This zone uses colder air and higher airflow. Air direction is tuned to hit the top and side surfaces evenly. If the top sets while the sides remain soft, the coat can slump and expose corners. The belt speed through this zone is set so the surface is firm by the time the piece reaches the first transfer point, where vibration or belt transitions could otherwise mark it. The next zones are slower. Chocolate needs time to crystallize through its thickness. If the core of the coating is cooled too abruptly, the outside contracts first and locks in stress. That stress shows up as microcracks, especially at sharp corners where the chocolate film is thin and stretched. It can also show up as a faint dullness or streaking that indicates crystal instability. Therefore, the tunnel profile often steps down gradually, with airflow reduced and temperature slightly higher than in the first zone, but still below the chocolate's setting range. Humidity control runs through the entire tunnel. If air is too humid, condensation forms on cold chocolate surfaces. Even invisible microcondensation can dissolve sugar dust and then recrystallize as bloom, creating a hazy finish. Humidity also affects the toffee core indirectly. Toffee is hygroscopic and will absorb moisture over time, softening its snap. The coating is a barrier, but any pinholes or edge exposures become moisture entry points. Keeping tunnel air dry reduces the risk of moisture being driven into microgaps as the bar cools and contracts. Exit temperature is chosen based on what happens immediately next. If the product goes into high-speed wrapping, the coating must be firm enough to resist scuffing and pressure marks from the wrapper film and folding guides. If it exits too warm, wrappers leave shiny rub marks and flattened edges. If it exits too cold, the toffee core becomes extremely brittle and can crack internally when pieces experience small drops or impacts. Internal cracks may not be visible, but they create more fines over time and lead to breakage in the pack. The tunnel, therefore, aims for a stable, handling temperature rather than the coldest possible temperature. Once the coating is set, the line typically adds a stabilization conveyor before packaging. This conveyor equalizes temperature between the surface and the interior of the bar. Chocolate is a poor conductor compared to metal tooling, so the core of the coating can remain warmer than the surface immediately after cooling. Equalization reduces residual stress and lowers the risk of later cracking when the bar experiences temperature changes. Equalization is also useful for products that will be stacked or bagged because pieces that are still slightly warm can stick at contact points even if the surface feels dry. At this stage, the line often rescreens the output. Even with careful dust control and gentle handling, some doubles, broken corners, and fines will appear. A gentle screening deck can separate loose chocolate droplets and small fragments from the main product. For bite-sized pieces, this screening step is important because small fragments migrate to the bottom of a bag and create a dusty, messy consumer experience. For larger bar segments, screening prevents fragments from contaminating wrapper seals. If the product format is a full bar rather than small coated pieces, there is an additional assembly path. Instead of coating many loose chunks, the plant can create a continuous toffee slab, cool it, then apply chocolate as a coating layer and cut the bar after coating. In this format, the chocolate curtain coats a continuous slab or a wide belt of pieces arranged tightly. A bottoming system lays down a continuous base. Air knives and leveling rollers smooth the surface. The slab is cooled and then cut into bars. The advantage is cleaner geometry and fewer exposed corners. The challenge is managing cut edges after coating, because cut edges expose the toffee interior. Some lines, therefore, use a side coating step or a second pass to seal cut edges. Others accept exposed edges and rely on barrier wrapping to slow moisture ingress. When almonds are present as a surface layer on the toffee, coating strategy becomes more demanding. Nut fragments create peaks and valleys. Peaks produce thin chocolate films that can pinhole. Valleys trap excess chocolate and create heavy pockets. The enrober may therefore run a slightly higher viscosity chocolate to build a thicker coat over peaks, then use air knives to remove excess without exposing those peaks. Cooling must then be tuned to prevent cracking around nut points where chocolate thickness changes rapidly. After stabilization, packaging becomes the long-term protection system. Chocolate-coated toffee is sensitive to moisture and to temperature swings. Moisture softens the toffee and dulls the snap. Temperature swings encourage chocolate bloom by destabilizing fat crystals. Packaging films are chosen for barrier properties. A higher moisture barrier slows water vapor ingress. A higher oxygen barrier helps preserve flavor notes, though the dominant concern for toffee is moisture and texture rather than oxidation. For individual wraps, flow wrappers form film around each piece and seal it with heated jaws. Seal parameters are tuned so they close without burning film and without heating the chocolate surface. Film tension is controlled to avoid scuff marks. The wrapper fold geometry is designed so sharp edges of the toffee do not puncture film. If the product includes small, sharp almond fragments near the surface, wrapper puncture resistance becomes more important. Some lines use a slightly thicker film or a laminated structure for this reason. For bag formats, the product flows into multi-head weighers. Flow performance depends on surface smoothness and lack of tack. If pieces are overcooled, they become brittle and generate fines during vibration and drops. If undercooled, they can stick and bridge in hoppers. Hoppers are designed with steep walls and low friction surfaces. Gentle vibration may be used, but excessive vibration is avoided to prevent breakage. The weigher builds portions by combining small hopper dumps and releases them into a vertical form-fill seal tube. Seal jaws close above and below the drop. Timing is tuned so pieces clear the seal zone, because a piece caught in the seal creates a leak. Case packing is designed to reduce abrasion and temperature exposure. Wrapped pieces are collated into cartons or placed directly into shipping cases. Cases are stacked to minimize compression on the bottom layer, because compression can fracture brittle toffee cores over time. Pallet patterns allow airflow in storage, so temperature remains uniform and avoids warm spots that soften chocolate. If the product will be stored for long periods, the plant relies on stable ambient temperature ranges that keep chocolate crystals stable. Large swings between warm and cool cause expansion and contraction. Expansion can stress the chocolate to toffee interface. Contraction can pull the chocolate away at corners and create microgaps. Those microgaps become moisture pathways. Stable storage reduces these risks and preserves snap. Butter handling is tightly managed before it ever enters the kettle. Melt temperature is held just high enough for smooth pumping, because overheated butter can separate into a thin fat phase and a heavier milk solids phase. If that separation enters the cook, milk solids can concentrate at hot surfaces and scorch, while free fat rises and makes the toffee greasy. Filtering the melted butter removes aggregates, so the emulsion forms predictably when butter is introduced into the concentrated syrup. Crystallization control is handled through syrup composition and through how the syrup is cooled. Corn syrup is metered precisely because it limits sucrose crystallization and keeps the finished toffee glassy. If corn syrup is too low, the cooked mass can grain as it cools and form a sandy texture. If too high, the toffee can become slightly more plastic and less brittle, reducing the sharp snap. The dissolving step is also important here because undissolved sugar grains act as nucleation sites that trigger graining later. Once the toffee is cast into a sheet, cooling uniformity determines internal stress. Uneven cooling creates layers with different brittleness, which fracture unpredictably and generate excess fines. To reduce this, cooling belts use consistent contact and controlled airflow. The line avoids cold drafts that set the top too fast, while the underside stays warm, because that locks in stress that later appears as spider cracking during breaking. Almond application is treated as a timed adhesion event. Almonds must land while the surface is tacky, and the distribution must be even, so the breaker sees a consistent thickness and stiffness across the sheet. If almond density varies, the breaker produces mixed sizes, and the screens return too much oversize for rework, which increases dust generation. Roasted almonds are cooled and held dry so they do not introduce moisture that would soften the toffee surface. Rework loops are kept deliberately small. Broken toffee pieces and edge trims do not behave like fresh sheet because their moisture history and fracture microstructure are different. Too much rework increases fines and creates bars that break in the wrapper. Plants therefore cap rework ratios and keep rework streams segregated by stage, so a heavily fractured stream is not fed back into a stage that expects intact sheet. Maltesers begin with a brittle malt center expanding into a tiny honeycomb sphere. The center is the part that makes the product different from an ordinary chocolate ball. It is light, crisp, and porous, with a dry snap inside a smooth milk chocolate shell. The manufacturing line is designed to build that contrast in stages. First the malted center, then the rounded shape, then the chocolate layers, then polishing, cooling, weighing, bagging, and final packing. The malt center starts as a cooked mixture. Malt extract, sugar, glucose syrup, milk ingredients, and other dry components are measured into a controlled batching system. The ingredients enter mixing vessels, where heat and agitation turn them into a thick syrup. The syrup must be uniform before it can be aerated and expanded. Malt extract gives the center its toasted, cereal-like flavor. It blends into the sugar system as the liquid warms. The mixture becomes darker, thicker, and more elastic. Agitators keep it moving so the sugars do not settle or burn against heated surfaces. The syrup then moves into a cooking stage. Heat drives off moisture and concentrates the sugars. The liquid becomes more viscous as water evaporates. Its temperature and solids level must reach the correct point, because the final texture depends on how the sugar structure sets after expansion. At this stage, the mixture is still dense. It has flavor, sweetness, and malt character, but it does not yet contain the light honeycomb structure. That structure forms when the cooked mass is expanded. Gas generation or aeration creates tiny cavities inside the hot sugar malt mixture. The expanding gas pushes through the softened mass, forming a network of bubbles. The bubbles stretch the syrup into thin walls. As the mixture cools, those walls harden into a crisp, porous structure. The material changes quickly. A heavy syrup becomes a lighter foam-like mass. It is not soft like whipped cream. It is a hot sugar structure full of trapped voids. When it sets, it becomes brittle and dry. The expanded malt mass is cooled and broken down into smaller pieces. It may be formed into rough pellets, cut, screened, or milled into controlled fragments before shaping. The goal is to create center pieces that can be rounded into small balls of consistent size. The pieces pass through sizing equipment. Screens remove fines and oversized fragments. Airflow can pull away light dust. The accepted pieces move into rounding equipment. The centers tumble inside rotating pans or drums, where their edges are gradually worn down. Rounding is slow and mechanical. The rough pieces roll against each other and against the drum surface. Corners break away. Flat faces soften. Each piece becomes closer to a sphere. Small additions of binding material or syrup may help the particles build a smoother surface as they tumble. The center does not need to be perfectly polished yet. It only needs the right size, shape, and strength for chocolate coating. If the center is too rough, the chocolate shell becomes uneven. If it is too fragile, it will break during panning. If it is too dense, the final bite loses the light Malteser's texture. The rounded malt centers move through a drying and conditioning stage. Warm air reduces surface moisture and stabilizes the texture. The centers must be dry before chocolate is applied. Moisture would interfere with coating and could make the chocolate grip unevenly. Before coating, the centers are inspected and classified. Small broken pieces are removed. Oversized centers are separated. Dust is screened away. A clean, dry stream of malt balls then moves toward the chocolate panning area. Milk chocolate is prepared in a separate system. Cocoa ingredients, milk powder, sugar, cocoa butter, and vegetable fat or other formula components are mixed and refined. The mixture passes through rollers that grind the particles smaller. Refining gives the chocolate a smoother mouthfeel by reducing the size of sugar and cocoa particles. After refining, the chocolate is conched. In conching machines, heavy mixing arms continuously move the chocolate for a controlled time. The process smooths the texture, distributes fat around the dry particles, and develops the final flavor. The chocolate becomes glossy, fluid, and uniform. The chocolate must then be tempered. Tempering controls how the fat crystals form. The chocolate is cooled and gently reheated through a precise temperature curve. This creates stable crystals that help the coating set with a clean finish. Proper tempering gives the shell firmness and reduces dullness or soft texture. The malt centers enter coating pans. These are large rotating drums, angled so the centers tumble continuously. A measured amount of tempered milk chocolate is sprayed or ladled onto the moving centers. The chocolate touches the dry malt balls and spreads as they roll. The first layer is thin. It seals the porous center and creates a smoother surface for later layers. The centers continue tumbling while cool air passes through the pan. The chocolate sets around each piece. Once the layer is firm enough, another small addition of chocolate is applied. The coating builds gradually. Maltesers are not coated with one heavy pour of chocolate. The shell forms through repeated thin layers. Each layer must spread, set, and bond before the next layer arrives. This creates a rounded, even chocolate covering without flooding the centers or joining them together. The sound inside the pan changes as the shell thickens. At first, the centers make a dry rattling sound. As chocolate builds, the movement becomes softer and heavier. The pieces roll over one another with a smoother, duller sound. The pan speed, air temperature, chocolate temperature, and addition rate all control the shell. If chocolate is added too quickly, pieces stick together. If air is too cold, the coating can set before it spreads. If air is too warm, the surface stays tacky. The machine balances movement, temperature, and timing until each ball reaches the correct size. After the main chocolate coating is built, the pieces continue tumbling to smooth the surface. Small ridges are evened out by rotation. The shell becomes more uniform with every turn. The pieces are now recognizable as Maltesers, but they still need finishing. A polishing stage may apply a very thin finishing layer. The pieces tumble while a glazing or polishing material is added in tiny amounts. This gives the chocolate surface a smooth, lightly glossy appearance and helps reduce scuffing during packaging. The finished pieces then move into cooling. They travel through a cooling tunnel or controlled room where air removes heat from the shell. The chocolate firms fully. The coating becomes stable enough for weighing, conveying, and bagging. After cooling, the Maltesers pass through inspection. Screens remove broken pieces, dust, and double pieces stuck together. Metal detection checks the product stream. Optical systems can detect unusual shapes, exposed centers, dull patches, or oversized clusters. Rejected pieces are separated from the main flow. The accepted pieces move into holding hoppers above the packaging line. The hoppers are designed to keep the chocolate pieces moving gently. Sharp drops are avoided because the coating can scuff or chip. Controlled gates feed the product into weighing systems. Multi-head weighers portion the Maltesers into exact amounts. The pieces fall into small weighing buckets. The control system selects the best combination of buckets to reach the target weight. Gates open and the measured amount drops into the bagging machine. For small bags, packaging film unwinds from a roll. The film passes over a forming collar and wraps into a tube. A vertical heat seal closes the back seam. The weighed Maltesers drop into the open tube. Horizontal sealing jaws close the bottom and top seals, forming individual bags. The sealed bag passes under a coder. Production information is printed onto the film. The bag then moves through check weighing. Any underweight or overweight pack is rejected automatically. For boxed formats, the pieces may be weighed into a bag first, then inserted into a carton. Flat paperboard blanks are opened into box shapes. The filled inner pack slides inside. Folding rails close the flaps. Adhesive or locking tabs hold the carton shut. Twix begins as a long sheet of biscuit dough moving toward a cutting line. The dough is built to become a crisp base. It must be strong enough to carry caramel, but light enough to snap cleanly under the chocolate shell. The process starts with flour, sugar, fat, leavening ingredients, salt, and water entering a controlled mixing system. Dry ingredients are weighed first. Flour flows from storage bins through enclosed conveyors. Sugar and smaller powders are added through separate dosing units. Each ingredient passes into a mixer in measured amounts. The mixer does not simply stir the powders. It builds a dough with the right texture for sheeting, cutting, baking, and coating. Fat is added to create the short, crumbly biscuit texture. It coats part of the flour and limits gluten development. This is what helps the biscuit break cleanly instead of becoming chewy. Water enters slowly, just enough to bind the dry ingredients. The mixer blades fold, press, and turn the mass until it becomes a firm dough. The dough exits the mixer in heavy pieces. It is fed into a hopper above a sheeting machine. Large rollers pull the dough downward and compress it into a thick sheet. The sheet passes through more rollers, each pair reducing the thickness. The surface becomes smoother with every pass. The dough sheet must reach a precise thickness. If it is too thick, the biscuit will bake slowly and make the bar heavy. If it is too thin, it can crack under the caramel layer. The sheeter controls the height with adjustable roll gaps. Once the sheet is even, it moves under cutting rollers. The rollers score and cut the dough into long, narrow biscuit fingers. Small holes may be docked into the surface. Docking lets steam escape during baking and helps prevent the biscuit from puffing unevenly. The shaped dough pieces transfer onto an oven band. The band moves continuously through a long baking tunnel. Heat surrounds the dough from above and below. Moisture begins leaving the biscuit. The surface firms first, then the center dries and sets. Inside the oven, the dough changes from pale and soft to golden and crisp. The fat melts, water evaporates, and the structure becomes rigid. The biscuit pieces shrink slightly as they bake. Their edges sharpen, and the surface develops a light toasted color. The oven has different temperature zones. The first zone sets the shape. The middle zones drive off moisture. The final zones finish the color and texture. The goal is a biscuit that is dry, crisp, and strong enough for high-speed handling. The baked biscuit fingers leave the oven and enter a cooling section. Air flows over and under the pieces. Cooling is important because caramel cannot be applied properly to hot biscuits. If the biscuit is too warm, the caramel may spread too much or soften the structure. The cooled biscuits travel in straight lanes. Conveyor guides align them precisely. The next layer is caramel. Caramel is prepared in a separate cooking system. Sugar, glucose syrup, milk ingredients, fat, and water are mixed in heated vessels. The mixture starts as a pale liquid. As it cooks, water evaporates and the sugars concentrate. The liquid thickens and develops a smooth, stretchy body. The caramel must be cooked to a very specific texture. It cannot be too runny, or it will flow off the biscuit. It cannot be too firm, or it will not deposit evenly. The finished caramel must hold its shape as a layer, but remain soft enough to bite through. After cooking, the caramel is cooled to a controlled depositing temperature. It remains warm and pumpable. Pipes carry it to the depositor above the biscuit lanes. The depositor contains nozzles matched to the spacing of the biscuits. As each biscuit passes underneath, a ribbon of caramel is laid along the top. The caramel lands as a smooth strip, following the length of the biscuit. The depositor times each flow so the caramel starts and stops at the right point. It must not hang over the ends too far, because excess caramel can interfere with chocolate coating. The caramel-topped biscuits continue forward. Cooling air firms the caramel surface. The layer becomes stable enough to move, but it remains soft inside. The product now has the basic Twix structure: biscuit base and caramel top. Some lines form the biscuit and caramel as long continuous strips before cutting. In that version, caramel is deposited onto long biscuit slabs. The slabs then pass through slitting and guillotine cutting systems that divide them into individual bars. The cutting blades must pass cleanly through caramel and biscuit without dragging the layers out of position. The formed bars are spaced apart before chocolate coating. Correct spacing matters because the enrober must cover every side without bars touching each other. Vibrating conveyors and timing belts create even gaps between the pieces. Milk chocolate is prepared in another part of the factory. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are blended into a chocolate mass. The mixture is refined through rollers that reduce particle size. This gives the chocolate a smooth texture instead of a gritty one. The refined chocolate is conched. Heavy mixing arms move the chocolate for a controlled time. The mass becomes smoother, more fluid, and more uniform. The fat coats the dry particles evenly. The chocolate develops the proper flow for coating. Before it can cover the bars, the chocolate is tempered. Tempering controls the crystal structure of the cocoa butter. The chocolate is cooled and warmed through a precise temperature curve. Stable crystals form, allowing the coating to set with a firm surface and clean snap. The Twix bars enter the enrober on a wire mesh belt. A curtain of tempered milk chocolate falls from above. Each bar passes through the curtain and chocolate flows over the caramel top, down the sides, and around the biscuit edges. At the same time, chocolate is applied from below. The mesh belt allows chocolate to coat the underside. The bar becomes fully covered. Excess chocolate drains through the belt and returns to the tempering system. After the curtain, the bars pass under air blowers. These blowers remove extra chocolate from the top and sides. The airflow smooths the coating and controls shell thickness. Too much chocolate would make the bar heavy and uneven. Too little would expose biscuit or caramel. The coated bars then pass over a vibrating section. The vibration helps remove trapped air bubbles and evens the chocolate surface. The shell becomes smoother as the bar continues forward. The surface pattern forms as the chocolate settles. Twix bars often have a slight ripple or flow texture on top because the chocolate curtain, airflow, and movement shape the coating before it sets. The ridges are not carved after cooling. They form while the chocolate is still fluid. The bars enter a cooling tunnel. Inside, chilled air circulates around them. The chocolate shell begins to crystallize and harden. Cooling must be controlled carefully. If it is too fast, the coating can become dull or crack. If it is too slow, the chocolate may remain soft and mark during wrapping. As the bars move through the tunnel, the shell changes from glossy liquid to firm chocolate. The caramel stays enclosed. The biscuit remains dry because the coating seals it from the outside. At the end of cooling, the bars leave the tunnel fully set. They pass through inspection. Cameras check shape, size, coating coverage, and surface defects. Metal detectors scan the product stream. Bars with exposed biscuit, missing chocolate, broken edges, or distorted caramel are rejected automatically. Accepted bars move toward wrapping. Twix bars are usually packed as paired fingers or single bars depending on the format. Lane systems align the bars and bring them into the required grouping pattern. For a twin pack, 2 bars are placed side by side with controlled spacing. The wrapper begins as a roll of printed film. The film unwinds and passes through rollers that control tension. It moves around a forming box, where it wraps around the bar or bar pair. The product enters the film tube in perfect timing with the print registration. A longitudinal seal closes the film along the back or underside. Heated sealing wheels, or jaws, press the film layers together. Then cross-seal jaws close the ends of each pack. The jaws seal and cut at the same time, separating one wrapped pack from the next. The process begins with the reception of raw cacao beans. These arrive in large burlap sacks, which are automatically tipped into a stainless steel hopper. The hopper feeds a vibratory conveyor, shaking the beans in a controlled rhythm to remove debris and small stones. As the beans travel, high-powered magnets and air jets eliminate metallic fragments and lighter contaminants. Once cleaned, the beans move into the roasting chamber. This is a horizontal, drum-style roaster with precise temperature zones along its length. The beans are roasted between 120 degrees Celsius and 150 degrees Celsius for 30 to 45 minutes, depending on origin and moisture content. Inside the rotating drum, baffles lift and drop the beans repeatedly to ensure even exposure to heat. The surface crackles as volatile acids are driven off, and the aroma intensifies. Roasting profiles are strictly controlled using infrared sensors and thermal probes. After roasting, the beans exit into a rapid cooling system, a double-jacketed air cooling tunnel that quickly brings the temperature down to prevent over-roasting. As the beans cool, they're conveyed to the winnowing station. Here, a precision cracking roller gently fractures the outer shells. The mixture then passes through an ascending air column. Shells, being lighter, are blown upward and extracted into a cyclone separator. The heavier nibs fall downward, separated cleanly. The nibs are then routed into the liquor grinding system. This involves a two-stage reduction process. First, a coarse grinder reduces the nibs into a paste-like mass using granite rollers. This mass, still gritty, feeds into a 5-roll refiner. The rolls are made from hardened steel and arranged in descending gap widths. The rollers spin at increasing speeds to shear the particles down to 20 microns. During this stage, the paste becomes smooth and glossy, now known as chocolate liquor. From the refiner, the liquor is pumped into a conching machine. This is a long, horizontal tank with heavy granite paddles. The paddles rotate slowly but forcefully, kneading the liquor for up to 72 hours. During this process, frictional heat raises the temperature to 50-60 degrees Celsius. This drives off unwanted volatiles and enhances texture. As it churns, the chocolate undergoes subtle flavor transformation and becomes fluid, velvety, and aerated. At this stage, additional ingredients are introduced through precision feeders. Sugar is added via a sealed screw conveyor that meters crystalline particles in carefully measured doses. Milk powder, if producing milk chocolate, is pre-blended with a small portion of cocoa butter before being added. The mix is tested repeatedly with inline viscometers and particle size analyzers to ensure consistency. Next, the chocolate moves into the tempering system. This consists of 3 stainless steel heat exchangers that rapidly cycle the chocolate through defined temperature curves. The liquid chocolate is cooled from 45 degrees Celsius down to around 27 degrees Celsius and then reheated to 31 or 32 degrees Celsius. This carefully controlled crystallization process encourages the formation of stable cocoa butter crystals, Form 5, which gives the final chocolate a glossy finish and crisp snap. Once tempered, the chocolate is ready for molding. It flows into automated depositor heads mounted above polycarbonate molds. Each head features multiple precision nozzles controlled by servo motors. The nozzles deposit exact volumes of chocolate into the cavities, synchronized with the moving mold belt below. Vibration tables mounted beneath the molds shake rapidly, eliminating trapped air and evening out the surface. The molds enter a cooling tunnel, a refrigerated corridor where temperature and humidity are tightly regulated. Inside, a chilled airflow passes over the molds for 10 to 15 minutes, bringing the chocolate down to 8-10 degrees Celsius. This solidifies the product and locks in the tempered structure. Once cooled, the molds are inverted and gently flexed by mechanical arms to release the solid chocolates. They drop onto a food-grade conveyor belt, which directs them to the decorating and enrobing section. Here, high-speed cameras inspect the chocolates for surface defects, rejecting any that are misformed or marred. If filled or layered chocolates are being produced, the process diverges earlier. In that variation, the molds receive only a thin chocolate shell in the first deposit. These shells are then cooled, filled with praline, ganache, or fruit paste through precision piston fillers, and then sealed with a final layer of tempered chocolate before full cooling. Back on the main line, the finished solid chocolates enter the enrobing tunnel if they require coatings. This consists of a continuously flowing curtain of tempered chocolate falling from a weir system. The chocolates pass beneath the curtain on a wire mesh belt, receiving a uniform coating. Excess chocolate is blown off the bottom by air knives positioned beneath the belt. After enrobing, the products move through another cooling tunnel. This secondary tunnel is slightly longer and maintains cooler airflow at 6-8 degrees Celsius to ensure the coating sets with a uniform sheen. Inside, multiple temperature zones gradually reduce the product temperature to avoid bloom or condensation. Next is the decorating phase. This station uses robotic arms fitted with ultra-fine nozzles and stampers. The arms are guided by a 3D vision system to identify the orientation of each piece. Depending on the product, they may apply fine chocolate stripes, edible gold dust, cocoa powder, or even embossed logos using heat press stamping heads. Some lines include a nut topping mechanism that drops single pistachios or almonds onto the still soft chocolate surface with pneumatic precision. From here, the chocolates move to the buffering conveyor. This is a serpentine belt that temporarily holds products in case downstream machines slow down or halt. It prevents product collisions and maintains production flow without pause. Once flow resumes, the chocolates proceed to the wrapping line. The wrapping process begins with a high-speed feeder system. Chocolates arrive in single file along a narrow conveyor aligned by adjustable guide rails. As they approach the wrapping unit, an optical sensor scans each piece to verify orientation and spacing. A star wheel indexing system captures each chocolate in a rotating pocket, ensuring it enters the wrapping machine at precisely timed intervals. For individually wrapped pieces, the wrapping style depends on the product type, either fold wrap, twist wrap, or flow wrap. Fold wrap is used for rectangular or square chocolates. A continuous roll of foil, ends, often metallized polypropylene or laminated aluminum, feeds into a cutting station. A servo-driven knife slices the foil into perfectly sized sheets. A vacuum picker transfers each sheet onto a wrapping plate where a chocolate rests. Pneumatic folders quickly tuck each edge of the foil around the chocolate with clean, creased folds. And heated plates press the final seam to ensure adhesion without adhesives. In twist wrapping, used for rounded or pillow-shaped pieces, the chocolates are dropped into film pockets on a rotating turret. As they spin, two heated jaws grip the ends of the film and twist them in opposite directions in a single, fluid motion. The result is a tight double twist at both ends with no glue, secured purely by friction and film memory. Flow wrapping is reserved for bars or longer chocolates. Chocolates move onto a horizontal flow wrapper in perfect rows. A forming box folds a continuous film web into a U-shape around the moving product stream. Longitudinal sealing wheels fuse the film along the bottom seam using heat and pressure. Rotary end sealers then crimp and cut between each chocolate in one continuous motion. The result? A tight, seamless pillow pack with serrated edges. Once wrapped, products pass under a metal detector integrated with an automatic reject arm. Any contamination triggers an immediate air jet that diverts the product off the main line without interrupting flow. Approved chocolates continue to the labeling and grouping section. For chocolates requiring labels or tamper-evident seals, a label applicator aligns pressure-sensitive labels onto the wrapper surface with micron-level accuracy. For sealed tags or holograms, a rotary arm applies the label with static discharge to eliminate air pockets. High-speed vision systems verify placement and orientation, rejecting any misaligned units. Next, the wrapped chocolates are grouped into sets for final boxing. This is handled by a Delta robot pick-and-place system. Using 3 arms mounted on a gantry and guided by overhead cameras, the robots lift chocolates from the conveyor and deposit them into plastic or cardboard trays. The trays are held on index pallets that move step by step beneath the robot's reach. Depending on the SKU, arrangements may be linear rows, nested pyramids, or offset diagonals. If the product is a boxed chocolate assortment, the process diverges again. Assorted trays begin with an injection-molded plastic insert, which is automatically placed into a folding carton. Chocolates are sorted by type and delivered to multi-head pickers. Each picker arm uses vacuum suction or soft rubber grippers to lift specific chocolates and place them in precise tray compartments. The sequence is synchronized to ensure correct assortment patterns. No duplicates, no gaps. Once loaded, these trays move to the lid application station. A folding carton blank is fed into a forming mandrel, where pneumatic fingers erect and glue the box around the insert. A transparent film or foil seal is sometimes heat applied across the top, shrinking snugly into place. Then, a decorative lid is pressed on with a spring-loaded arm to achieve a flush seal. If a rigid luxury box is used, an entirely separate line assembles it. Die-cut cardboard is laminated with printed paper and hot-pressed into box forms. Magnets or ribbon closures are inserted automatically by articulated tools. The finished boxes are then transferred via robotic arm to receive their filled trays. From here, final boxing and case packing begins. Chocolates, now individually wrapped or boxed, arrive on a wide accumulation belt. Automatic collators organize them into bundles of 6, 12, or more, depending on shipping unit configuration. These bundles are pushed into carton erectors where flat corrugated blanks are folded around them, glued and pressed shut. Some lines use wraparound case packers. In this method, the grouped products are held stationary as a blank corrugated sheet is wrapped around all sides. Mechanical arms fold the flaps, apply hot melt glue, and compress the bundle into a sealed shipping case. These cases exit onto a short conveyor where industrial inkjet printers mark each side with batch numbers, timestamps, and QR trace codes. The case is then moved to the palletizing zone. Here, a robotic arm with a vacuum plate or gripper head arranges cases onto pallets. Each layer follows a programmed stacking pattern, alternating orientations for stability. After each layer, a slip sheet may be inserted by an automated feeder. Once the full stack is complete, often up to 2 meters high, the pallet is conveyed to a stretch wrapping machine. The stretch wrapper features a rotating turntable and a film carriage that moves vertically. As the table spins, the carriage stretches and applies multiple layers of plastic film under tension. This secures the load tightly and protects against moisture and dust. Some systems include a top sheet applicator that lays a waterproof plastic sheet across the top before wrapping. Finally, the fully wrapped pallets are conveyed through a weight check station and scanned by a vision system for final verification. They are now ready for shipment. A precisely manufactured, delicately handled series of chocolates transformed through over 24 distinct mechanical stages from raw bean to boxed luxury. For filled and layered chocolates, the factory employs a specialized multi-stage molding line. This system operates on a closed-loop conveyor that continuously cycles polycarbonate molds through a sequence of precisely timed stations. Each mold contains multiple cavities, and every station in the circuit performs a distinct action in the assembly of complex, filled products. The process begins with the shell forming station. A depositor head releases a measured volume of tempered chocolate into each mold cavity. Immediately, the molds move to a tilting station, where they are flipped and vibrated simultaneously. Centrifugal force causes the chocolate to coat the sides and bottom of each cavity evenly, leaving a hollow center. Any excess chocolate flows out and is reclaimed. After inversion, the molds pass under a chilled airflow, rapidly setting the shell. Once the shell is solidified, the molds continue to the filling station. This unit features servo-controlled piston depositors mounted above each cavity. The fillings are stored in heated hoppers to maintain fluid consistency. These can include hazelnut praline, fruit compotes, flavored ganache, caramel, or nut pastes, each delivered through dedicated nozzles. The depositors lower and inject precise quantities into each chocolate shell without disturbing the walls. Viscosity is controlled via inline heating coils wrapped around the filler lines. Every filling passes through mass flow meters to ensure consistency across thousands of units. Between each product type, CIP, clean-in-place systems, purge the lines with high-pressure heated water, followed by compressed air to eliminate cross-contamination. Next, the filled molds pass through a brief cooling tunnel. This lowers the filling temperature just enough to create a thin surface skin, ensuring it doesn't mix with the final chocolate seal. At the cap sealing station, another depositor head applies a top layer of tempered chocolate, sealing each cavity shut. This chocolate is deposited with high precision, covering the filling completely and fusing to the shell edges. Vibration tables beneath the molds remove trapped air and ensure a flush finish. The molds then enter a long cooling tunnel, typically spanning over 10 meters. This tunnel contains multiple chilled zones that gradually reduce product temperature from 30 degrees Celsius to under 10 degrees Celsius. The slow, staged cooling prevents shrinkage or cracking and allows the chocolate to fully contract away from the mold walls. Once cooled, the chocolates are ejected mechanically. Pneumatic plungers behind each mold cavity gently push the finished pieces downward onto a soft conveyor. These filled chocolates proceed to surface treatment. For layered chocolates, a similar system is used with key variations. After the first shell is deposited and cooled, a layer of inclusions, such as crushed nuts, cookie pieces, or fruit granules, is sprinkled into the mold by an oscillating vibratory feeder. A light pressure roller presses the inclusions into place. Then, a layer of filling is added, followed by a capping layer of chocolate. This creates a tri-layered cross-section when cut or bitten. Aerated chocolates follow a different method entirely. Here, the chocolate is first fed into a pressurized vacuum chamber. Under controlled vacuum, nitrogen gas is injected into the chocolate stream through a sparger, a perforated titanium rod. The gas forms microbubbles, which are then locked in by suddenly returning the chamber to atmospheric pressure. The now aerated chocolate has a mousse-like texture, yet remains stable once cooled. This aerated mixture is deposited into molds using modified volumetric heads that prevent bubble collapse. Because of the internal gas structure, aerated chocolates are cooled more gently to avoid rapid contraction. They pass through a specialized tunnel with fine-tuned temperature gradients that stabilize the internal structure. Some advanced variations include dual flavor split molds. These use two separate depositors operating in tandem, each filling half of the mold cavity with a different chocolate, such as milk and white or dark and ruby. A precision divider plate inside the nozzle ensures a clean, vertical split. The chocolates are deposited simultaneously, then vibrated and cooled, just like single origin types. Another variant involves inclusions in the chocolate itself. Before deposition, the base chocolate is mixed with particulate ingredients in a jacketed mixing bowl. These include puffed rice, freeze-dried fruit bits, chopped nuts, or biscuit crumbs. Agitators inside the bowl maintain even suspension. A positive displacement pump pushes the mixture through a large bore pipe to prevent clogging. Depositor heads with wider nozzles are used to handle the textured mass. For decorative layering, some lines use transfer film technology. A thin acetate film, printed with edible cocoa butter designs, is cut into sheets and placed on the bottom of each mold before chocolate is deposited. When the chocolate sets, the design transfers from the film onto the chocolate surface, creating intricate visual patterns. After cooling, the film is peeled away, leaving behind a vivid imprint. In other cases, chocolate pieces are stamped with embossed patterns or logos. After demolding, the chocolates move under a stamping head fitted with a heated metal die. The die is pressed lightly onto each piece, embossing it with a brand mark, pattern, or crest. The metal stamp is kept at 32 degrees Celsius, just warm enough to soften the surface without damaging structure. At this point, finished chocolates, whether filled, layered, aerated, or decorated, are directed toward the enrobing and topping station, if required. Some filled pieces receive an extra chocolate shell by passing through the enrobing curtain. Toppings such as sea salt flakes, crushed pistachios, or cocoa nibs are dispensed through multi-channel feeders synchronized with the belt speed. Each topping module includes a vibration sieve that controls granule size and drop rate. Sensors monitor belt occupancy to ensure no topping lands between products, minimizing waste. A gentle pressing roller may follow to embed toppings into the soft coating before cooling. Some premium chocolates are dusted with edible luster dusts or shimmer coatings. These powders are dispensed in an ultra-fine mist using electrostatic sprayers. The particles are positively charged as they exit the nozzle, adhering uniformly to the negatively charged chocolate surfaces. This creates a metallic or pearlescent finish with minimal overspray. For chocolates that require a hard shell glaze, a final step involves a rotating drum polisher. Chocolates are fed into the drum, which tumbles them gently while applying a thin mist of food-grade shellac or gum arabic. Internal warm air jets dry the glaze instantly, leaving a glossy, protective surface. Before reaching packaging, all finished chocolates pass through a multi-stage inspection tunnel. This includes laser-based shape detection, surface color analysis, and infrared temperature scanning. Products outside tolerance limits are ejected into designated bins. The final stage begins at the primary packaging line, where individual chocolates are grouped, positioned, and inserted into final, retail-ready formats. This step varies depending on the packaging style: rigid boxes, folding cartons, sleeve wraps, trays, tins, or multi-compartment assortments. Each format requires a dedicated configuration of pick-and-place systems, folder gluers, and sealing units. For rigid box assortments, chocolates arrive on an indexed belt and are picked by high-speed Delta robots equipped with vacuum suction heads. These robots place the chocolates into thermoformed plastic inserts, which are held stationary within open-bottomed rigid boxes. The inserts have precisely molded cavities matched to the contour of each chocolate piece. The robot arms adjust their speed and angle using dynamic feedback from overhead 3D scanners to avoid any misalignment. Once all cavities are filled, the boxes proceed to a film sealing station. Here, a roll of transparent BOP film is unwound, cut into sheets, and laid across the surface of the tray. A heated sealing plate presses the film into place, fusing it along the box edges to create a tamper-evident, airtight seal. The temperature of the sealing head is closely monitored by embedded thermocouples to maintain optimal adhesion without distorting the tray. For folding cartons, a different approach is used. Flat carton blanks, pre-printed and die-cut, are fed from a magazine stack into a carton erector. Mechanical arms fold the blank along pre-scored lines and apply hot melt glue in strategic points using precision nozzles. The forming mandrel compresses the carton into shape as it moves along the conveyor. Simultaneously, chocolates are grouped upstream by a collator belt, which aligns them into patterns matching the carton's internal layout. A pneumatic pusher slides each group into the open cartons as they move past. Once filled, the top flaps are folded and glued shut in a continuous motion. Some cartons are sealed with ultrasonic bonding, especially when glue-free closures are preferred. Specialty packaging formats, like sleeve-wrap trays, begin with a plastic or cardboard tray filled with chocolates using robotic placers. A printed sleeve, flat and folded, is then placed over the tray. A servo-controlled banding unit wraps the sleeve snugly and applies a heat pulse to seal the overlap. These sleeves often include die-cut windows or embossing, requiring precise alignment during application. For metal tins or embossed boxes, an overhead conveyor delivers empty tins into position beneath the filling heads. Chocolates are stacked by robotic arms, using multi-head grippers that rotate to fit varied geometries. Once filled, the tins are lidded by a lid placement mechanism equipped with pneumatic actuators. The lid is pressed into place with a calibrated force to ensure a snug fit without warping the metal structure. In premium lines, inserts and accessories are added next. These include product guides, tasting menus, or promotional leaflets. A sheet feeder places the inserts into each box before final closure. In some configurations, a robotic arm adds a protective paper layer or a foil cover between the chocolates and the lid. When ribbon closures are required, a secondary robot wraps and ties the ribbons automatically using twin spindle tensioners and soft grippers. After primary packaging, products move into the overwrapping unit, especially for premium and seasonal items. A continuous film roll feeds through a forming collar to enclose each box. A fin sealer applies pressure and heat along the bottom seam, while side sealers tuck and seal the ends into neat folds. A cooling plate downstream sets the film structure immediately after sealing. Optional tear strips or easy open tabs are applied at this stage. These are pre-cut film sections with embedded threads or adhesives that allow consumers to open the product without tools. A precision applicator adds them just before the film is sealed, embedding them into the plastic without disturbing box integrity. Next is batch labeling and coding. An inkjet printer or laser etcher marks each box with its batch number, manufacturing date, expiration date, and unique identifier. For export products, a vision verification system checks every printed code in real time and compares it against the product database. Any mismatch causes an automatic ejection by a pneumatic diverter. Then, boxes enter the case packing line. A robotic case packer arranges the boxed units into shipping cartons according to a pre-programmed pattern. Each case is assembled from flat blanks in an automatic erector. Once filled, the case is sealed using a high-speed tape applicator or hot melt glue system. The type of seal depends on the distribution channel and climate conditions expected during transit. Some boxes are stacked vertically, while others lie flat, depending on product fragility and presentation. If protective dunnage or air cushions are required, an integrated dispenser adds these into the case before sealing. Completed cases are printed with destination codes and passed through a check weigher, which confirms that each box is within expected weight tolerances. At the end of the line, full cases are transferred to the palletizing system. A robotic palletizer uses a vacuum plate or mechanical gripper to stack the cases onto pallets in a staggered pattern. The stacking sequence is designed for maximum load stability. Between layers, corrugated slip sheets are automatically inserted from a magazine. Once the pallet reaches the target height, typically 1.8 to 2 meters, it is conveyed to a stretch wrapping machine. The turntable rotates the pallet while a film carriage moves vertically, wrapping it in multiple layers of stretch film. Tension sensors ensure that the film applies consistent pressure without crushing the product. For export pallets, a top sheet dispenser adds a final moisture barrier before wrapping is completed. The final wrapped pallet moves to the finished goods staging area. Here, each pallet passes through a scanning tunnel that records its dimensions, weight, and barcode data into the warehouse management system. Automated guided vehicles, AGVs, retrieve the pallets and deliver them to temperature-controlled storage areas where ambient humidity and temperature are monitored continuously. In some specialized lines, climate conditioning is introduced post-packaging. Products enter a controlled chamber that simulates various storage conditions. For instance, rapid temperature cycling from 10 degrees Celsius to 30 degrees Celsius to ensure product stability. Chocolates are held in this chamber for several hours before release to shipping to verify that they maintain integrity under stress. Before release, a final quality sampling system selects random units from each production batch. These samples are conveyed to a physical and sensory testing station, where robotic arms manipulate the products through breakage resistance tests, surface gloss readings via reflectometers, and cross-sectional scanning via laser slicers. The internal structure is analyzed for air pockets, alignment of layers, and crystallization consistency.